Hello and welcome to this video about an introduction to graphs and graph neural networks. This video is a general introduction, so we are going to explore the fundamental concept of graphs, and we are going to delve into the world of graph neural networks, or GNN. So let's get started. Graphs are a powerful mathematical structure used to represent relationships between objects. They consist of nodes, or some call them vertices, and edges. Node represents entities or elements, while edge indicates the connection or relationship between them. The graphs find application in various domains such as social network, recommendation system, bioinformatics, and transportation networks. So as you might have guessed, the Uber, Google, the Instagram, any large scale application that you're seeing in today's world uses the graph because they are so useful and they are so capable. Graphs can be categorized into different types based on their characteristics. Some common types include the undirected graph, and we are going to explore these graphs in the later video. If this is just a brief introduction, and the undirected graph is an undirected graph. As the name suggests, the edges have no direction and the relationship between nodes is symmetric. Moving on to the directed graph. In a directed graph, the edges have a specific direction, indicating the one-way relationship between the nodes. We have the weighted graph. In a weighted graph, each edge is assigned to a weight or value representing the strength and the importance of the relationship between the nodes. Moving on to the bipartite graph. The bipartite graph is a graph that can be divided into two disjoint sets of nodes with edges only connecting nodes from different sets. Moving on to the graph neural networks. Graph neural networks are a class of machine learning model specifically designed to operate on the graph structured data. GNN extend the traditional networks to efficiently capture and process information from the nodes and their interacted relationships. GNN consists of several key components. The node feature. Each node in a graph has been associated with features or attributes such as the numerical value, text, or categorical variables, which provides information about the node characteristics. Moving on to the graph conventional layers. The GNN utilizes the graph conventional layers to propagate and update information between the connected nodes. These layers enable the GNN to learn the representation that captures both local and global graph structure. And we have the aggregation functions. GNN employ the aggregation functions to gather information from the neighboring nodes and incorporate it into the node representation. Common aggregate functions include summation, averaging, and max pooling. And the graph pooling is another aspect, which is the process of downsampling a graph by aggregating multiple nodes into a single respective node. It helps to reduce the computational complexity and extract a higher level feature. Moving on to the applications of the graph neural networks. Graph neural networks have gained significant attention due to their ability to efficiently model relational data. They find application in various domains, including the social media, network analysis. GNN can uncover the community structures, detect influential nodes, and predict missing connections. common in the social networks. And we have the recommendation systems, which are a pretty big part of graph neural networks, and GNN can enhance the personalized recommendation by capturing the complex user item interaction and leveraging the underlying graph structure. Moving on to the drug discovery, which is nowadays a pretty big deal. GNN show a promising result in predicting molecule properties and accelerating the process of drug discoveries. And traffic prediction is another aspect that Google uses this technology in their system a lot. GNN can analyze transportation networks, predict traffic flow, and optimize the route planning for efficient commuting. And there are challenges and future directions that the graph neural networks can go. While the graph neural networks have shown a great potential, there are several challenges and future direction that exist. First is scalability. Deploying a scalable GNN architecture can handle larger scale graph efficiently is in the ongoing research area. We have the graph generation. Generating a realistic graph that captures the complex relationship it is crucial for training and evaluating the GNN. We have the interpretability is another aspect that enhancing the interpretability of the GNN is essential to understand the underlying reasoning and decision-making processes. And the robustness is another aspect that it is weak in graph neural networks. Ensuring the robust of the GNN against the adversarial attacks and noisy data is a critical consideration, because not many people can design a system that is able to defend against these type of attacks. And in summary, the graphs provide a powerful framework for representing relationship, and graph neural networks offers us a unique approach to learn from the graph structured data. With their versatility and broad application, GNN are proven to be exciting, and they have advantages for many different areas of medicine, technology, and many places that even we still did not cover. So I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next. Hello and welcome to this video about graph terminology. In this video we are going to explore and expand upon the knowledge you have about the terminology surrounding the graph, and it's pretty essential to know these topics, especially nowadays with the growth of machine learning. Many beginners don't know the terminologies and they just dive into the code and they don't understand what is going on. So I hope this video gives you a solid understanding of the graph terminology. The graph neural networks, or GNN, are a class of deep learning models designed to process and extract information from the graph structured data. Graphs consist of nodes and vertices, and they connect by edges, representing relationship or connection between the entities. GNN excel at the computing dependencies and patterns such as interconnected data. The node, edge, and graph. To comprehend the GNNs, we must first understand the fundamental elements of graphs. Nodes are the individual entities within the graph, while the edges represents the connections or relationship between these nodes. These structures are the core concept of graph neural networks, enabling them to reason about complex dependencies. The graph convolutional network, or GCN, are one of the most popular architecture in the realm of the graph neural networks. GCN extends the concept of convolutional neural networks to graphs, enabling the propagation of information across the node base on their neighboring nodes. This allows CGN to capture local and global patterns in a graph structured data. We have the message passing and aggregation. Message passing and aggregations are a crucial operation in GNNs. In the graph neural networks, nodes communicate with their neighboring nodes by enhancing information or messages. This process allows each node to update its own representation based on the information it retrieves. The aggregation techniques such as summing or averaging are applied to combine these messages and produce a refined representation for each node. Moving on to the graph pooling, which is an essential technique in graph neural networks for downsampling graphs. It is similar to pooling layers in a traditional convolutional neural network. Graph pooling helps to reduce the size and complexity of the graph while preserving the important information, and it enables GNN to handle graph of varying sizes and hierarchies efficiently. We have the GAT or Graph Attention Network. The Graph Attention Network or GAT introduces an attention mechanism to graph neural network inspired by the success of attention in natural language processing, which we covered in the previous course. The GAT assigns the different important weights to the neighboring nodes during the message passing. This enables the GAT to focus on the more relevant information and attend to the important patterns of the graph during the computations. In the line next, the graph embedding is another key aspect, which the graph embeddings are a low-dimensional vector representation that captures the structure and the relational information of nodes in the graph. They enable the efficient processing and analysis of the graph structured data. Various techniques such as graph sage, graph isomorphism networks, and the graph convolutional networks are used to learn these embedding. Moving on to the graph classification and node classification. The graph classification and node classification are a common task in graph neural networks, and the graph classification involves assigning a label or category to the entire graph, while the node classification focuses on the producing labels for individual nodes. GNN can leverage the power of graph neural networks to achieve high accuracy in this classification task. And we have the graph generation. The graph generation is another fascinating application of graph neural networks, in my opinion. By learning from existing graphs, GNN can generate new graphs to exhibit a smaller structural characteristic. This capability opens the door to various domains such as the molecular generation in drug discovery and graph synthesis in social analysis. Well, graph neural networks have shown the great promise. They are still challenged to overcome. Scalability, efficiency, and handling large graphs are pretty difficult, and the advances are continued in these areas, and it will for sure drive the future of graph neural networks. And that concludes our journey through the terminology of the basic graph neural networks. We explored the nodes, edges, and graph structure. We learned about the graph convolutional networks, message passing, graph pooling, graph attention network, graph embedding, classification, and graph generation. So make sure to watch the later videos as well and stay focused. That's it for this video. I hope this video was informative to you, and if you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video. In this video we are going to take a look at graph representation learning, which is a technique that is kind of revolutionary in this field and brings together the power of graphs and machine learning to understand complex relationships and patterns in data. We will explore the fundamental techniques and application of graph representation learning that have a potential to revolutionize the domain field. So the graphs are a powerful data structure used to represent and model relationship between entities. They consist of nodes representing entities and edges and denoting connection or interactions between these entities. Graphs can be applied to diverse domains such as social network, biology, recommendation system, and much more. Each node and each edge in the graph can be associated with various attributes, providing rich information for analysis. However, analyzing graph directly can be complex and computationally intensive. This is where graph representation learning comes in rescue. Graph representation learning is a set of techniques that converts complex graph data into continuous vector representation or embedding. These embedding capture essential structure and semantic information from the graph, enabling traditional machine learning algorithms to work seamlessly on the graph data. The goal of the graph representation learning is to project nodes and their relationships into a low-dimensional space, preserving crucial network properties and patterns. This process allows us to perform tasks like node classification, link prediction, and graph cluster efficiency. Graph representation learning enhances various techniques, each categorizing to a specific challenge in the graph analysis. Where are some popular methods? So here are some popular methods. We have the node embedding, which in this method we have the random walk based method, deep walk, node to vec, graph SAGE, and normal graph neural networks. And in the graph neural networks or GNN, we have the message passing, graph convolutional networks, graph attention networks, and graph isomorphism networks or GIN. And also we have the graph autoencoder methods, and they include the variational graph autoencoders, which stands for VGAE, and we have the graph SAGE autoencoder. And these techniques utilize different mechanisms to encode the graph structure, leveraging neighborhood information and graph connectivity. The application of graph representation learning are vast and continually they are being expanded. So let's explore some real-world scenarios where graph representation learning plays a crucial role. We have in the areas of social network analysis, the community detection, influencer maximization. We have the influence maximization and anomaly detection. In the world of recommendation system, we personalize the recommendations, and we have the collaborative filtering. Moving on to the biological networks, we have the protein interactions prediction, and we have the drug target interaction. There are also other areas such as entity linking and relation extracting. The future of graph representation learning is incredibly promising. As researchers continue to innovate, we can expect advances in scalability, efficiency, and ability to handle large and more complex graphs. This will unlock new possibilities across domain and drives the groundbreaking discoveries. And in this video, we embarked on the journey through the world of graph representation learning, from understanding the basic graphs to exploring the techniques and patterns techniques and application that makes it a game changer in data analysis. Remember, with the power of graph representation learning, we can unlock the hidden insights buried within the interconnected world of us. And that's it for this video. I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next Hello and welcome to this video where we are going to implement a graph convolutional neural network from scratch using PyTorch. GCN are a powerful type of neural network designed for processing graph structured data. They have been successfully applied into various domains such as social network analysis, recommendation systems, and biology, and many other more. So without further ado, let's dive into the code and see what we wrote right here. I'm going to explain to you every single line, so don't worry. And in the line 1 up to line 7, here we imported the libraries. First, we imported the NumPy library as an alias of NP. Secondly, we imported the torch, which is our PyTorch library, which provides us a flexible and efficient platform for building neural network and performing automatic differentiations. Moving on to the line 3 that says torch.nn, import as nn. We here import the neural network layer class from class and functionalities. It will help us to define and create layers of our GCN model. We imported as an alias of nn, which stands for neural network, and torch.optimum as optim. This one provides us with various optimization algorithm. We will use it to update the parameters of our GCN model during the training process. And the import network x as nx. Here the network x library provides us with a powerful tool for working with graphs and networks in Python. We will use the network x to generate a graph for our GCN demonstration. Moving on to the line 6, here we import the matplotlib as a PLT. Here we are importing the matplotlib library, which is widely used for plotting, which is a widely used plotting library in Python. We will use this to visualize the graph and get the result of our GCN model. Moving on to the line 7, here we import the torch.nn.fundamental as f. Here we will use this module for activation functions and other operation in our GCN model. And moving on to the graph convolutional class that we have in the line 9, here we define a new class named graph convolutional that inherits from the nn.module. This class will represent the building block of our graph convolutional layer. Moving on to the line 10, here we have the constructor of the graph convolutional class. It initializes the instance variable of the class when an object is created. The parameter in features and output features represent the dimensions of the output and features respectively. In the line 11, the super function here, super method, here we construct the parent class nn.module using the super function. This ensures that the graph convolutional class inherits all of the properties and modules of the nn.module. Moving on to the line 12, here we define a linear layer nn.linear and assign it to the instance variable self.linear. This layer will perform the linear transformation of the input features with the specified input and output dimensions. Moving on to the line 14, here this method defines the forward pass of the graph convolutional class, which describes how the input flows through the layer during the computation. Moving on to the line 15, this line performs the matrix multiplication torch.matmul between the adjacency matrix ADG and the input features, which is x. This step represents the graph convolutional operation where the features of the neighboring nodes are aggregated. Moving on to the line 16, here we apply the linear transformation defined in the constructor to the aggregated features of X. This step introduces a nonlinearity and allows us to model and learn more complex relationships in graph. Moving on to the line 17, finally we return the output X from the forward pass of the graph convolutional layer, and moving on to the GCN class. Here we defined another class called the GCN, which inherits from the GNN.module. This class represents the complete graph convolutional network, and in the line 20 the constructor of the GCN class takes two parameters, the n features and n classes. These parameters represents the dimension of the input features and the number of output classes respectively. Moving on to the line 21, here similar to before we create and call. Here we call the constructor of the parent class the GNN.module to inherit from its properties and methods. Moving on to the line 22, here we create an instance of the graph convolutional class which says self.conv1 with the n features as the input dimension and 16 as an output dimension. This represents the first graph convolutional layer in our GCN model. Moving on to the line 23, here we create another instance of the graph convolutional class self.conv2 with the 16 as an input dimension matching the output dimension of the previous layer and the n class as the output dimension. This represents the second graph convolutional layer in our GCN model. Moving on to the line 25, similar to graph convolutional class that we had, this method defines the forward pass of the GCN class. Moving on to the line 26, here we pass the input features X and the adjacency matrix ADG through the first graph convolutional layer self.conv1 to obtain the intermediate features of X. Moving on to the line 27, here we have applied the reflected linear unit ReLU activation function to introduce the nonlinearity to the intermediate features X. ReLU sets all negative values to 0, which helps the model learn complex patterns. In the line 28, here we apply the dropout regularization to the intermediate features of X using the fDropout function from the torch.nn.functional. The dropout randomly sets the fraction to 0.5 in this case of the input elements to 0 during the training to prevent overfitting. Moving on to the line 29, here we pass the modified intermediate features of X and adjacency matrix of ADG through the second convolutional layer self.conv2 to obtain the final output features of X. Moving on to the line 30, here that says return X. Finally, we return the output features of X from the forward pass of the GCN model. Moving on to the line 32, here this line defines the function named generates synthetic data that generates synthetic data that generates a synthetic graph data for our demonstration. The function takes an optional parameter num nodes, which specifies the number of nodes in the generated graph. Moving on to the line 33, inside the generate synthetic data function, we create a random geometric graph using the nx.randomGeometricGraph function from the network X. This function generates a graph where nodes are placed randomly in a unit square and two nodes are connected if their Euclidean distance is within the specified radius, in this case 0.2. Moving on to the line 34, here we convert a generated graph G to its adjacency matrix representation using the nx.toNumPy function. The adjacency matrix represents the connection between the nodes as binary matrices. The line 35, here we convert the adjacency matrix ADG to a PyTorch tensor using the torch.tensor. This step ensures that we can perform efficient computations on adjacent matrix using the PyTorch. And in the line 36, 37, here we generate a random feature vector for each node in the graph using numpy np.random and .rand function. The feature vectors have dimensions of num nodes and 2. In the line 38, here we convert the feature vectors to a PyTorch tensor, similar to what we did with the adjacency matrix. This allows us to perform computation on the features using PyTorch. And in the line 40, we randomly assign labels to each node in the graph using the numpy np.random.radiant function. The labels are binary, taking the values of 0 and 1. And in the line 41, here we convert the vector labels to a PyTorch tensor. The dtype equal torch.long argument specifies that the labels are of the long integer data type. Moving on to the line 42, here return G features ADG and label. Here the generate synthetic data function returns the generated graph G feature vectors of features adjacency matrix ADG and the label vector labels as a tuple. Moving on to the line 44, def train model. Here we define a named train model that trains our GCN model. The function takes 5 parameters: the model, the GCN model to train, the features, which is the input features, ADG, the adjacency matrix, and the label, which is a ground truth label, and the optional parameters, epochs, which is the number of training epochs, defaulting to 100. Moving on to the line 45, optimizer =optim.atom. Here inside the train model function, we create an atom optimizer using the optimum.atom class from PyTorch. The torch.optim module is a class from the PyTorch torch.optim module. The atom is the optimization algorithm commonly used for training neural network. We pass the model.parameters to specify the parameters to optimize. LR1 equals 0.01. It is to set the learning rate and the weight decoy 5e-4 for weight decoy regularization. Moving on to the line 46, here we define the loss function for our GCN model. Here we use the nn.crossentropy loss class from the PyTorch, the torch.nn module, which is from the PyTorch.nn module, and the cross entropy loss is suitable for multi-classification problem, which in this case we have 2 classes 0 and 1 in our label, so this is good for that. And in the line 48, we start a loop that iterates over the specified number of epochs for training the model. The loop variable epochs keeps the track of the current epochs number. Moving on to the line 49, here we set the model training mode using the train method. This step is necessary when we are using certain layers such as dropout that behave differently during the training and evaluation. Moving on to the line 50, here we zero out the gradient of the model parameters using the zero grad method of the optimizer. This step is essential for computing the gradients in each training iteration. And in the line 51, here we pass the input features and their adjacency matrix ADG through the GCN model to obtain the logits, which is the model raw output from each node. Moving on to the line 52, here we compute the loss by comparing the logits obtained from the model with the ground truth labels using the cross entropy loss function, the criterion, and the loss represents the discrepancy between the model predictions and the true labels. Moving on to the line 53, here we perform the back propagation to compute the gradients of the model parameters with respect to the loss, the gradients are computed automatically using PyTorch automatic differentiation compatibilities. Moving on to the line 54, here we update the model parameters by calling the step method of the optimizer. The optimizer adjusts the parameter based on the computed gradients and the chosen optimization algorithm, in this case Atom. Moving on to the line 56, here we use an if statement to check if the current epochs is multiple of 10. This condition allows us to print the training process every 10 epochs. Moving on to the line 57, here inside of the if statement we print the current epoch number and the corresponding loss value item loss.item using the f string. This provides a process of update during the training. At the line 59, here we define the function named visualize graph that is used to visualize the graph and predict labels. The function takes 4 parameters: the g, which is the graph, the labels, which is the ground truth label, the labels, which is the predicted labels, and an optional parameter title, the title of the visualization, defaulting to graph convolutional network. Moving on to the line 60, here we have here inside of the visualize graph function we receive the node position from the graph G using the ng.get node attribute function. The position are stored in the node as the node attribute under the key pose. The line 61, here we create a new figure for the visualization using the plt.figure from the matplot library. The fixed size equal 8 and 6. Argument specifies the width and height of the figure in inches. Moving on to the line 62, here we use the nx.draw function from the network X to draw the graph G. The pose parameter specifies the node position. In this case the node size is the 300. Sets the size of each node, and the node color equal pred labels assigns the color to the nodes based on the predicted labels. The C map equal plt.cm.rdylbu specifies the color of map to use, and the labels equal true displays the node labels. Moving on to the line 63, here we set the title of the plot to the specified title using the plt.title. We can change it to anything that we want, but I did not do that. plt.show is pretty obvious. This will display the plot using the plt.show. This command shows the graph visualization on the screen. Moving on to the line 66, here we generate a synthetic graph data by calling the generate synthetic data function, and the trunk and the return values of the unpacked into variables G, features, and the ADG, also the labels. This variable represents the generated graph. Feature vectors add adjacency matrix and the ground truth label respectively. The line 69 GCN, here we create an instance of the GCN class with the n features equal to and the n classes equal to. This creates a GCN model with the input feature dimension of 2 and the output class dimension of 2. Moving on to the line 70, here we call the train model function to train the GCN model using the generated features ADJ and the label as a training data. These steps perform the training process for the specified number of epochs. Moving on to the line 73, here we set the GCN model in its evaluation mode using the eval method. This step is necessary when we want to use the model for interface or evaluation, as it disables the certain layer behaviors such as dropout. Moving on to the line 74, here we enter a width block using the torch.nograd context manager. This blocks allow us to perform computation without keeping the track of the gradient. It improves the efficiency when we don't need gradients during the interface or evaluation. And moving on to the line 75, here we pass the input features and the add adjacency matrix ADG through the trained GCN model to obtain the logit, the model raw dropout for each node. Moving on to the line 76, we calculate the predicted labels by taking the index of the maximum value along the dimension of 1 of the logit tensor using the torch.argmax. The resulting tensor is then converted to a numpy array using .numpy for the capability with the visualization function. Moving on to the line 76, here we call the visualize graph function to visualize the graph along with the grounded truth label and the predicted labels. This step generates a plot that shows the graph visualization with the color node representing a predicted label. So let's run the code and see the final output, and as you can see, this is our result. It's pretty cool. In this video we covered the process of implementing the graph convolutional networks from scratch. I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video. In this video we are going to take a look at the fascinating concept of graph neural network, and to be specific we are going to take a look at how message passing works and discuss the significant applications of it. Before we dive into the message passing, let's briefly understand what graph neural networks are. GNN are a type of neural network architecture designed to process and analyze data represented in a form of graphs. These graphs consist of nodes, also called vertices, and edges, also called connections, and links that connect these nodes. GNN are a powerful model that can capture complex relationships and dependencies among the nodes in the graph. Moving on to the message passing. Message passing is a fundamental operation in GNN that enables information exchange between the connected nodes within the graph. It allows nodes to communicate with their neighbors, gathering information from graph or a structure and update their own representation based on this information. In order to perform message passing, each node and edge in the graph needs to have a representation. Node representation encode the features or attribute associated with the node, while the edge representation captures the relationship between the connected node. These representations serves as a basis for message passing operations. Moving on to the message passing process. The message passing process consists of two fundamental steps: the message computation and aggregation. During the message computation, each node structure manages the combining its own relationships with the representations of its neighboring node. This message is then passed to the neighboring node for aggregation. Moving on to the aggregation and update. The aggregation involves combining the received messages from the neighboring node to create a summarized representation of the node neighborhood. This aggregated representation is then used to update the node own representation. The update step typically involves applying a readable function or activation function to aggregate the representation. Message passing is often performed iteratively, allowing the nodes to define their representations over multiple rounds of communication. In each iteration, the messages are exchanged and aggregated, and the node representation are updated. This iterative process enables GNN to capture complex dependencies and higher order relationships in the graph. There are several various message passing in GNN, each with their own characteristics and applications. Some common variants include the graph convolutional network, graph attention network, network, graph SAGE, and the graph isomorphism network. These variants differ in terms of message computation and aggregation options, and message passing in GNN has found application in various domains, including the social network analysis, recommendation systems, drug discovery, computer vision, and natural language processing. GNN have demonstrated their effectiveness in tasks such as node classification, link prediction, graph generation, and high-level prediction. While the message passing in GNN has shown great promise, there are still challenges to overcome, which include the scalability, handling dynamic graph, and designing the architecture of GNNs, which are pretty difficult and still a new topic to explore. So in summary, message passing is a vital operation in graph neural networks, enabling information flow and communication between the nodes in the graph. It empowers the GNN to capture its interactive relationships and dependencies, making them a powerful tool for graph learning tasks. So I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about graph pooling and graph attention mechanism. In this video, we are going to take a look and explore the fundamental of graph pooling and graph attention mechanism. Before we dive into the graph pooling and graph attention, let's quickly recap the concept of graph. Graph is a mathematical representation that consists of nodes connected by edges. These nodes and edges can model complex relationships, making the graph an excellent tool for analyzing data with interactive dependencies. The graph neural networks, or GNN, have revolutionized the way we handle graph structured data. They extend the traditional network diagram to handle graphs, enabling us to process and extract useful information from unstructured data. In the traditional convolutional networks, pooling operations help reduce the spatial dimensions and capture the most relevant features. Similarly, in GNN, graph pooling serves a similar purpose. It aggregates and summarizes information from neighborhood nodes to a higher level representations, helping to handle graphs with varying sizes and complexities. There are different types of graph pooling techniques, each with their own approach to selecting their representative node or subgraphs. Some common methods include the top K pooling, selecting the top K node based on the certain criteria. We have the graph coarsening, which is to aggregating nodes from a coarser graph representation. We have the diff pool, using the differentiable module to learn node importance and construct a hierarchical representation. And the graph attention mechanism are a crucial statement in enhancing GNN performance. They allow a model to focus on important nodes while performing message passing through the graph. The graph attention mechanism works similar to the attention mechanism in natural language processing. They assign attention weights to nodes during the message passing, allowing the model to prioritize certain node information over others. This way, the GNN can learn which node are more relevant to a specific task, landing improved performance and better generalization. And let's let's explore some common types of graph attention mechanism. We have the graph SAGE, which is the aggregate information from the neighboring node using the weighted sum approach. We have the JET, which is the graph attention network itself, and it uses a self-attention mechanism to assign different weights to the neighboring node. We have the LGAT, large content graph attention network, that incorporates additional content beyond the direct neighbors from the enhanced attention. And the combination of the graph pooling and graph attention mechanism has shown remarkable result across various domains, including the social media network analysis, drug discovery and molecule property predictions, recommendation system, traffic prediction, and image and point cloud data analysis. So in conclusion, the graph pooling and graph attention mechanism plays a crucial role in advancing the capabilities of the graph neural networks. They enable the efficient processing of graph structured data, making them a valuable tool in various real-world applications. I hope you found this video insightful and informative. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about node classification using graph neural networks. In this video we are going to take a look at the concept of node classification, which is pretty important to know, and in recent years node classification using graph neural networks are gaining popularity more than ever. So let's dive into the interactives of these techniques and explore how it works. To comprehend the node classification using graph neural networks, first let's understand the fundamental concept behind it. A graph neural network is a deep learning architecture especially designed to incorporate on a graph structured data. It can extract valuable information from the nodes and their relationships. The node classification refers to a task of assigning labels or categories to a node in the graph. By leveraging the power of graph neural networks, we can predict the labels of the unbalanced nodes based on the information available from the label nodes. And the graph neural networks excel at capturing the inherent structure properties of a graph, allowing us to make accurate predictions about the nodes. They consider both the local neighborhood and the global structure, enabling them to capture relationships and dependencies within the graph. So let's explore the architecture of a typical graph neural networks used for neural classification. At its core, it consists of multiple layers, each performing operations on the node representation. These layers define the information gathered from the neighborhood of each node, gradually incorporating more global information as the network deepens. The key concept behind the graph neural network is the message passing. In this process, each node aggregates and updates the representation by incorporating information from the neighboring nodes. Through multiple inheritance of the message passing, the network gathers and refines information, allowing for increasingly accurate node classification. Training a graph neural network for node classification involves two main steps: the forward pass and the back propagation. In the forward pass, the network propagation message message through the graph. In the forward pass, the network propagates the message through the graph, updating the node representation instance, the back propagation step calculates the loss between the predicted and the true labels and then adjusts the network parameters to minimize this loss and optimization performance. The utilization of graph networks for node classification offers us several significant benefits. Firstly, it can handle graphs of various sizes and structure, making them applicable for a wide range of real-world problems. Secondly, these networks can efficiently model the complex dependencies between the nodes. Second, enabling accurate prediction even in the scenarios with the interact relationship. Lastly, graph neural networks can leverage both node feature and graph structure, extracting valuable information from these both sources to improve the classification performance. The node classification using neural networks has found application in various domains such as social network analysis, recommendation system, bioinformatics. Researchers continue to explore the new ways to enhance the performance of these networks and apply them to increasingly complex problems. So in conclusion, node classification using graph neural networks is a powerful technique that can enable us to accurately classify nodes within the graph by leveraging the structure properties and the complex relationship present in the graph. These networks open up the new possibilities for understanding and analyzing various domains. So I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching and I will see you in the next video. Hello and welcome to this video about graph classification in graph neural networks. In this video we are going to dive into the world of graph classification and explore its significance and techniques and real-world application. Graphs are a versatile structure that represents connections between the entities, such as social network, biological systems, and recommendation engines. Graph classification aims to categorize these graphs based on their structure properties and underlying patterns. There are different types of graphs. Graphs come in various types, including the directed, undirected, and weighted and unweighted graphs, also cyclic and acyclic graphs. Each type provides a unique insight into different domains and application. The graph classification finds application in diverse fields. For instance, the social network analysis, it helps us to identify the communities and influencers. In bioinformatics, it is aid in the protein structure prediction and drug discovery and plays a crucial role in recommendation systems such as fraud detection and network security. The graph classification it is built on top of the mathematical foundations, leveraging the concept from linear algebra, graph theory, machine learning algorithm, and graph kernels, and graph neural networks and graph-based feature extraction techniques are some of the key methodologies employed in this process. The graph classification pipeline consists of several stages. It starts with the pre-processing. While graphs are cleaned and normalized and transformed into suitable format, the feature extraction follows, where relevant graph-based features are computed and machine learning models and then trained using these features to classify the graphs accurately. Graph classification techniques vary based on the characteristics of the problem at hand. Methods such as support vector machines, decision trees, random forests, and deep learning architectures like graph convolutional networks and graph attention networks are commonly used to tackle graph classification challenges. The graph classification challenge has led to remarkable achievement in various domains. It has helped to predict disease patterns, detect anomalies, financial networks, detect anomalies in financial networks, optimize the supply chain logistics, and enhance personalized recommendation system. The ability to uncover the hidden sites within the complex graph structure that has revolutionized the way data analysis works. There are many outgoing researches and futures planned for the graph classification and graph neural networks, so stay tuned for them in the field. And graph classification provides us with a lens through which we can better understand complex pattern systems and uncover hidden insight. By harnessing the power of graph analysis, we can navigate the interconnected world with the greater clarity and make more informed decisions and impact the lives of others. So that's it for this video. I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about link prediction using the graph neural networks. In this video we are going to take a look at the concept of predicting the link, and which enables us to uncover hidden relationships, identifying potential collaborations, and improve the recommendation systems. So in this video we are going to take a look at all of them, but first we are going to discuss what is the link prediction. Link prediction is a process of interfering, missing, or feature connections in a network graph. It involves analyzing the topology and characteristics of the existing network to predict the likelihood of the existence of the certain links. The link prediction has numerous applications in social media networks, recommendation system, biology, and more. There are challenges in link prediction. The link prediction faces several challenges, such as the presence of a noisy data, limited information, complex network structure. Traditional methods often struggle to capture the high dimensional and non-linear patterns preserved in a large-scale graph. These are where the graph neural networks come into play. The graph neural networks are a class of deep learning model specifically designed to handle graph structured data. GNN have gained immense popularity in recent years due to their ability to capture complex dependencies and extract meaningful representation from the graphs, and the GNN leverages the message passing and aggregation techniques to learn node and edge embedding, which captures the structural and contextual information of the graph. Several GNN based techniques have been proposed for the link prediction, which include the graph convolutional network, the graph SAGE, graph attention network, and many other theories are right now in the internet, and their scientific papers are being published, so make sure to search that as well. And the link prediction using the graph neural networks gives us a powerful framework for uncovering hidden connection within the network graph by leveraging the GNN and combining them in features. Combining them with feature engineering technologies, you can achieve more accurate link prediction in a wide range of applications. As the field link prediction continues to advance, the GNN will undoubtedly play a vital role in discovering the hidden relationship and shape our interconnected world. So that's it for this video. I hope this video was informative to you and you learned something from it. If you have any questions, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about graph generation using the graph neural network. In this video we are going to take a look at the graph generation and explore how the graph neural networks plays a vital role in this process. The graph generation refers to an automatic creation of graphs of data structure composed of nodes and edges. These nodes and edges can represent a wide range of entities and their relationships, such as social network, the chemical compound, or recommendation system. Graph generation is a fundamental task in various domains, facilitating the creation of the new data instances that follow certain patterns or distribution. It is particularly meaningful when dealing with the limited data or for data augmentation. The graph neural networks are class of deep learning model designed explicitly for processing graph structured data. Unlike the traditional neural networks, GNN can operate directly on graph, leveraging the inherent connectivity and information to make predictions and discover new knowledges. GNN have revolutionized the field of graph-based machine learning by enabling the model of complex dependencies and interactions with the graphs. They have found application in diverse areas, including node classification, link prediction, and of course the graph generation. The graph generation with GNN typically involves two primary approaches: the autoaggressive and variational. The autoaggressive model, in this approach the graph is generated sequentially, node by node or edge by edge at each step. The GNN generates one part of the graph conditioned on the previously generated component, ultimately constructing the entire graph. We have the variational model. These models are inspired by the variational autoencoders and focus on the generating graph in a latent space. A GNN encodes an input graph into a latent representation, which is then used to sample new graphs by following the learned distributions. And both of these approaches have their strengths and trade-off depending on a specific requirement task. While the graph generation using GNN is a powerful tool, it comes with a set of challenges with majors. One major is dealing with incomplete graphs where certain nodes or edges are missing. The GNN must learn to handle such situation and generate a meaningful graph despite the missing information. Another challenge lies in the generating graph with the specific properties or structures. For instance, in molecular chemistry, we might want to generate a valid chemical compound with the desired properties. Achieving this requires a careful design and fine-tuning of the GNN model. And in conclusion, and to sum this video up, graph generation using graph neural networks is a captivating field with far-reaching implication across various domains. GNN ability enables us to understand more complex graph structure, empowering us to generate new data instances, unlocking the novel possibilities for research, analysis, and data augmentation. Whether it's creating chemical compound or generating realistic social networks or any other graph related task, GNN provides us with a very powerful tool so we can use it creatively and explore the vast world of graphs and make different ideas come into the reality. So that's it for this video. I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching and I will see you in the next video. Hello and welcome to this video. In this video we are going to take a look at graph neural networks for recommendation system. Recommendation system come into rescue by leveraging cutting edge technologies like graph neural networks to deliver personalized and efficient recommendation. Today we will dive into the fascinating world of graph neural networks for recommendation systems. We will explore how these powerful algorithms revolutionize the way we discover, explore, and connect with the products and clients. So at its core, recommendation systems are an intelligent algorithm that analyzes user behavior, preferences, and the historical interactions to suggest relevant items or content, and these systems strive to predict the user interest accurately and deliver personalized recommendations, enhancing the user experience and driving engagement for businesses. Before we dive into the graph neural networks, let's briefly touch on the traditional recommendation system. Collaborative filtering and content-based filtering have been the cornerstone of such systems. For years, collaborative filtering relies on the user-item interaction, while content-based filtering leverages the item attributes. However, these methods can often face challenges with the data sparsity and cold start problem. The graph neural network have emerged as a groundbreaking approach to address the limitation of the traditional recommender systems. GNN thread the recommendation problems as a graph representation where users and items become nodes and interactions from the edges. This unique architecture allows GNN to capture complex relationships, user-item dynamics, and discover the latent pattern that could be otherwise challenging to uncover. On the fundamental building block of graph neural networks is the graph convolutional networks that enables information propagation through the graph aggregation and features from the nodes to update the representation of each node iteratively. This process allows GNN to model dependencies and interactions among users and items more efficiently. In addition to GCNs, other GNN architecture like Graph SAGE and Graph Attention Network have gained popularity in recommendation systems. Graph SAGE and SAGE employs a sampling to scale large graph, while the GAT introduces the attention mechanism to emphasize the important connections, enabling better personalized recommendations. The cold start problem, which occurs when a new user or item lacks sufficient historical data for recommendation, poses a significant challenge. GNN excel at addressing this issue by leveraging the graph-based information and propagating signals across similar user items. This empowers recommendation system to make informed recommendation even for new users and items. Graph neural networks have been demonstrated an impressive ability and scalability and also the efficiency to handle large-scale recommendation system. By leveraging the parallel processing optimization, GNN can process vast graphs efficiently, ensuring the real-time recommendation even in high-demand scenarios. One of the key strength of the graph neural networks is the ability to provide highly personalized recommendation by capturing the interactive relationship and user preferences. GNN powered recommender system can deliver tailored suggestion, enhancing the user satisfaction and engagement. Graph neural network for recommendation system have found extensive application across diverse domains, from e-commerce platforms to stream services and social media platforms. GNN are a powerful, intelligent recommendation engine, enabling users to discover relevant products, movies, music, and even connect with like-minded individuals. As the technology continues to evolve, the graph neural networks hold the immense potential to revolutionize the recommendation system even further, with ongoing research search and advertisement, we can get even more accurate, interpretable, and content over recommendation, paving the way for truly personalized digital experience. Graph neural networks for recommendation system empower businesses to deliver personalized recommendation, revolutionizing how we discover, engage, and connect with the world of products and the digital world in general. So that's it for this video. I hope you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about heterogeneous data in graph neural networks. Graph neural networks have emerged as a powerful tool for analyzing, processing graph structured data, while traditional GNN have primarily focused on the homogeneous graphs. Recent advancements have extended these models to handle graphs with heterogeneous data. In this video, we will explore the concept of handling graph with heterogeneous data in GNN, and we will discuss the various aspects of it in detail. In graph, node and edges have different types of attributes, leading to the heterogeneous data. For example, in social network graph, node can represent user, while edge can represent different types of relationships, friendships, family ties, etc. Additionally, nodes and edges have associated with attributes like user profile, instant interest, or timestamp. Heterogeneous data introduces a complexity in modeling graph structured, requires specialized techniques in GNN, and dealing with the heterogeneous data in GNNs presents several challenges. Some of these challenges include the heterogeneous feature representation. Nodes and edges with different types of attributes require appropriate feature representations to capture their unique characteristics. Message passing across heterogeneous nodes is another aspect. In traditional GNNs, message passing was straightforward among the homogeneous nodes. However, in this case, heterogeneous graphs and designing message passing schemes that consider the different types of node become a crucial aspect. Aggregation and pooling is another aspect. Aggregation information from the diverse node and edges types while preserving the heterogeneity is a non-trivial task. Developing efficient aggregation and pooling techniques is essential to aggregate for accurate and meaningful representations. Heterogeneous graph alignment is another aspect which aligns the various types of node and edges to enable meaningful comparisons and computation, which is a key challenge to handle heterogeneous data. Techniques for handling heterogeneous data are several, so I'm going to explain to you a couple of them. To address the challenges mentioned, researchers have proposed several techniques for handling graph with heterogeneous data in GNN. Some permitted techniques are heterogeneous graph embedding, the transferring heterogeneous data into low-dimensional embedding, where each dimension captures a specific information about the node or edge type. This enables unified computation across different types. The heterogeneous message passing, the designing message passing mechanism that considers the heterogeneity of the node and the edge types. This involves the developing of the specific message function and carefully aggregating and uploading node representations. Heterogeneous graph attention, which is a way of incorporating attention mechanism into a with the important different node and edge types during the information propagation and aggregation. And we have the heterogeneous graph pooling here. Proposing pooling techniques that can serve the heterogeneity of the graph while capturing the most salient information across different types. There are many applications for handling heterogeneous data in GNN. The ability to handle graph with the heterogeneous data has a wide range of application, including the social media analysis, which we diversity relationship, user attribute, and the behavior pattern. And the recommendation system, obviously, it is incorporating multiple types of user item in heterogeneous, such as rating, reviews, and textual information to enhance personalized recommendation. Biological and chemical networks is another application which we model complex biological and chemical networks with various types of node and edges to understand the interaction and the functional relationships. And the knowledge graphs are also an application that is less known, which is expanding the knowledge of graphs into incorporate heterogeneous data sources and enrich entity relationships. So in summary, handling graphs with heterogeneous data in GNN is a crucial research area that enables the analysis of the complex graph structure with a diverse node and edge type. By addressing the challenges and employing the socialized techniques, GNN can efficiently model and process heterogeneous graph data, leading to advancement in various domains. Remember, this field is an ongoing field and it's being developed every single day, so make sure to research this topic with the latest data and Google it and use other platform to get the latest advancements. So that's it for this video. I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching and I will see you in the next video. Hello and welcome to this video about graph alignment and matching. In this video we will explore the concept of graph alignment and matching, and we will explain various aspects of it in detail. Graph alignment refers to the process of finding a correspondence or mapping between the nodes and edges in two or more graphs. It aims to identify similar structure and establish relationships between them. This technique is widely used in various domains including the bioinformatics, social network analysis, image processing, and data mining. And graph alignment is important. It is pretty important because it enables us to compare and analyze the structured similarity between the different graphs. While aligning graphs, we identify the common patterns and extract meaningful information to get insight into complex data. This process helps in tasks such as the protein structure comparison, the social analysis, and pattern recognitions. There are several techniques that have been developed for graph alignment, such as with their strength and limitations. So let's explore some of them. We have the subgraph isomorphism, which is a technique that involves finding the exact subgraph match between the two graphs. It aims to identify the subgraph in one graph that it is isomorphic to subgraph in another graph. It is computationally intensive approach but guarantees an exact match. We have the approximate graph matching. This technique focuses on the finding approximate matches between the graph considering the structure and attribute similarities. It relaxes the requirement of finding an exact match and allows for some level of this similarity. And we have the network alignment. The network alignment techniques aim to align multiple graphs simultaneously. They consider the global structure and connectivity pattern to find the correspondings between nodes across different graphs. It's particularly useful for aligning larger scale networks. The graph alignment poses several challenges due to the complexity and diversity of graphs. Some common challenges include the scalability. The aligning larger scale graphs with millions of nodes and edges can be computationally expensive and time consuming. We have the noise and incompleteness, which is a big problem in the real world projects. Graphs often contain nodes missing data, incomplete information, which makes alignment more challenging. Sometimes we even have the wrong data in our system, so that raises a big problem. We have the heterogeneity. The graphs can have different types of nodes and edges. Aligning each heterogeneous graph requires specialized techniques. Graph alignment has numerous practical applications. Here are a few examples. The biological network analysis. The graph alignment helps in comparing biological networks such as protein-protein interactions networks, gene regularity network, and metabolic network. It aims in understanding evolutionary relationships and identifying fundamental similarities and discovering new biological insights. The social network analysis graph alignment techniques can align social networks to identify common communications, influential areas, and informative flow across different platforms. Image and video analysis is another aspect. The graph alignment it is used in computer vision to align and match features in image or video. It consists of object recognition, image retrieval, and video summarization. So graph alignment and matching is a powerful technique for comparing and analyzing a structured similarity between the graph, and it helps uncovering hidden relationships, extracting valuable insight, and solving complex problems across various domains. By aligning graphs, we can enhance our understanding of complex data and make informed decisions. So that's it for this video. I hope you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about graph neural networks in reinforcement learning. In this video we will dive into the world of graph neural networks and explore how they revolutionize the field of reinforcement learning. Reinforced learning is a branch of machine learning that deals with decision-making environments, unlike supervised learning where algorithm is provided with the labeled examples, or unsupervised learning where it finds patterns in unlabeled data. Reinforcement learning operates in an interactive setting. The agent interacts with an environment, takes action, receives feedbacks in the form of rewards, and learns to maximize its cumulative reward over time. The graph neural network are a class of neural network especially designed to process graph structured data. Graph are a mathematical structure composed of nodes and edges representing entities and their relationships respectively. The GNN enables us to incorporate and inherit a structural information of the graphs into learning processes. In reinforcement learning, GNN are employed to process a state transition graphs, and each node in the graph represents a state, and the edge captures the possible transaction between the states. And one of the fundamental components of the GNN is a convolutional networks. GCN adapt the concept of convolution, which is widely used in the image processing to graph data. When GCN processes a node in the graph, it aggregates information from its neighboring node and applies a learnable transformation to update its own features. This process is iteratively performed for all nodes, allowing the network to capture complex dependencies and propagate information throughout the graph. And the key idea behind the GNN is message passing. Each node communicates with its neighbors by passing messages which contain information about the node features. This communication mechanism allows GNNs to share information across the entire graph and collectively make better decisions. By leveraging the graph structure, GNN can efficiently handle scenarios where the relationship between the state is crucial for making decisions such as navigating maze, playing the board games, or controlling robots in the complex environment. Reinforcement learning often encounters graph with various sizes and complexities. To handle such cases, GNN employ the graph pooling techniques, and graph pooling techniques aggregates multiple nodes into a similar representative node, reducing the graph size while preserving the essential information information. This process helps GNN to scale a larger graph and improve their efficiency in handling complex tasks. Another variant of GNN used in the reinforcement learning is graph attention network. Graph attention network introduces a concept of attention mechanism to assign different weights to the neighboring nodes during the message passing. The attention mechanism allows GNN to focus more on the relevant nodes, emphasizing the crucial state and actions while filtering out the nodes that are less informative, that filtering out noise or less important information. This attention graph approach significantly enhances the performance of the GNN in various reinforcement learning tasks. The graph neural networks have found numerous applications in the reinforcement learning, offering several benefits, which is the representation learning. GNN excel at capturing complex relationships and dependencies among the state in the graph. By efficiently encoding the graph structure, GNN can learn rich representation that captures essential information for decision making. We have the generalization. GNN generalize well to unseen graph structures, allowing them to adapt different environments and scenarios. This generalization capability is crucial when dealing with dynamic evolving environment, and there is efficient information sharing, which through the message passing, GNN efficiently propagate information across the graph, enabling nodes to benefit from their neighboring knowledge. This information sharing mechanism helps GNN to make informed decisions based on a collective intelligence, and there is handling irregular structures. Graphs can handle exhibit in irregular structures such as varying numbers or nodes or connectivity patterns. GNN can handle such irregularity efficiently, making them suitable for diverse reinforcement learning scenarios. GNN leverage the graph pooling techniques that helps scalability, which is another aspect, and these techniques help to scale to a larger graph by aggregating nodes. GNN can reduce the computational complexity while preserving the crucial information needed for decision making. The graph neural networks have merged as a powerful tool in reinforcement learning, allowing us to model complex interaction and dependencies in a graph structured data. By incorporating the graph inheritance structure, GNN can provide a robust framework for tracking challenges and reinforcement learning tasks. So that's it for this video. I hope you learned something from this video. If you have any question, put it down in the comments below. Make sure to leave a thumbs up button and subscribe. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about graph attention transformers. In this video, we are going to take a look at the concept of graph neural network and graph attention transformers. In recent years, graph neural networks have emerged as a powerful tool for modeling and analyzing complex structured data. One notable advancement in this field is graph attention transformer, or GAT. In this video, we are going to explore the key concept behind the GAT and how we can leverage it to use how it leverages the transformer architecture to improve the graph-based machine learning task. At its core, GAT is the representation of the graph of the data as graph. A graph consists of nodes which represent entities and edges, and they represent the relationships between these entities. The flexible representation enables GAT to handle a wide range of applications such as social network analysis, recommendation systems, bioinformatics, and many other more. The attention mechanism is a fundamental component of the GAT. It allows the model to assign different weights to different nodes in the graph based on their relevance to each other. This attention-based weighting scheme enables GAT to focus on the importance of the nodes while ignoring the less relevant ones, efficiently capturing the local and global dependencies within the graph. GAT incorporates the transformer architecture which has revolutionized the natural language processing task. The transformer architecture relies on self-attention, enabling of the model to capture dependencies between different positions in the input sequence. In the concept of GAT, the transformer architecture is adapted to handle graphs, enabling efficient and scalable graph processing. We have the multi-attention. GAT employs the multi-head attention to enhance its representational capability by using multiple attention heads. GAT can capture different aspects of the node relationships simultaneously. Each attention head is independently computes the attention weight and outputs from all of the heads that are then combined to create a more comprehensive representation of the graph structure. The GAT is trained using the combination of supervised learning optimization techniques. It leverages the labeled examples to learn the optional weights for its parameter. Statistical gradient descent and backpropagation are commonly used for optimization, allowing GET to interactively update its parameters and improve the performance on the graph-related task. There are many applications of GAT. GAT has found application in various domains: a social media network, predict the influential users, detect communities, and in the recommendation systems. GAT model user item interacts to provide personalized recommendation. In bioinformatics, GAT can analyze molecular graph for drug discovery and protein interaction predictions. Graph attention network. Graph attention transformers have become a significant breakthrough in the graph neural networks by incorporating attention mechanism and transformer architecture. The GAT can efficiently model complex relationships within the graph structured data, leading improved performance in various real-world applications. So that's it for this video. I hope this video was informative to you and you learned the basics of GAT. The graph attention networks are gaining popularity nowadays, and stay tuned for their advancements in their technology. Make sure to follow the news in this area on a monthly basis at least, and I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching and I will see you in the next video. Hello and welcome to this video about Graph Autoencoder. In this video we are going to take a look at the Graph Autoencoder, the theory, the implementation and visualization, and we are going to use tensor. We will dive into each and every single line and I will explain to you in detail so you have a good understanding of the code logic and architecture, and don't make these topics for yourself a big deal. These are pretty easy to understand. Of course, if you have programming experience. Without programming experience, you are unable to understand these, but if you have some programming experience, these are pretty easy, especially when I explain it to you. After watching this video, make sure to write down the code yourself and make some changes to better understand and work with the code yourself to better learn and memorize the concepts that I'm going to explain to you. So a graph autoencoder is a neural network architecture designed for graph data. It takes the input graph, compresses it into a low-dimensional embedding or an encoded representation, and then reconstructs the original graph from this compressed representation. This process allows the model to learn important features from the graph structure, which can be useful for numerous applications like node classification, link prediction, and graph generation. Now let's dive into the code itself and discuss each and every single line in detail as I told you. So in the line 1, we imported the NumPy library as an alias of NP, and NumPy is a fundamental library in Python for scientific computing and offers a comprehensive mathematical functions, random number generators, linear algebra, routines, Fourier transform, and many other that I currently don't remember, but it's a pretty useful library, and we are going to use it to create efficient and large-scale multidimensional arrays and matrices of numeric data. In the line 2 here, in this line, we import the two class from the TensorFlow.keras.layers module, the input and dense. The input class, it is used to instantiate a Keras tensor, which will act as a placeholder for our model inputs. The dense class represents a fully connected layer, which will be used in the building of layers of our autoencoder. In a dense layer, each neuron receives an input from all the neurons in the previous layer, hence is a fully connected. And moving on to the line 3 here, we are importing the model class from the TensorFlow.keras.module.models module in Keras. A model is a way to organize layer. It is especially useful when we are building complex model like autoencoders, which involve multiple interconnected layers. We will use it to build, compile, and train our models for the graph autoencoder. Moving on to the line 4 here. In this line, we are importing the plotly.graph objects, and we are assigning alias of Go or Go for short to the plotly graph objects, which these are a high-level interface to create a graph visualization. And in the line 5 here, we import the make subplots function from the plotly.subplots module. This function is a helper utility for creating complex subplots in the plotly. We are using it to create a multi-panel figure where each panel will be visualized a different stage in our graph autoencoding process. Moving on to the line 7 up to line 12 here, these line introduce a new class, graph autoencoder, and the class are a way of grouping together related data and functions which operate on them. This is, in this case, the graph autoencoder class. It is going to encapsulate all data and method related to our autoencoder. Moving on here in the line 8, this constructor method for this is a constructor method for the graph autoencoder class. This method is automatically called when we create a new instance of the graph autoencoder. It takes one parameter basis the mandatory self, the encoding dime, and the encoding dime, which this parameter will determine the dimensionality of our autoencoder bottleneck layer. And moving on to the line 9 here, we are sorting the value of the encoding dime as an instance variable, which means it will be accessible to all method of the class. This value will be used later when we construct our autoencoder. Moving on to the line 10 here, we are initializing a variable encoder as none. This instance variable will later be used to hold our encoder model. This encoder is the part of autoencoder that compasses the input into a latent space representation. Moving on to the line 11, similarly to the previous line, we are initializing a variable decoder as none. This instance variable will be used to hold our decoder model. The decoder is a part of the autoencoder that reconstructs the input from the latent space representation. Moving on to the line 12, this line initializes the autoencoder instance variable as none. This variable will be used later to store the full autoencoder model, which is the combination of the autoencoder and decoder. And in the line 14 here, we define a method build autoencoder. This method is responsible for building the structure of our autoencoder model. It takes num nodes as an input, which represents the number of nodes in the input data, in this case a graph. And in the line 15 here, in this line we create create the input layer from our model. The input function is used to instantiate a keras tensor that will be used as an entry point into our model. It takes one argument, which is the shape of our input. Here it's a tuple indicating that our input will be a one-dimensional array of length equal to the number of nodes. Moving on to the line 16, here we are defining a fully connected dense layer that represents the encoding part of our autoencoder. The number of neurons is equal to self.encoding time, and these neurons use the ReLU refactored linear unit activation function, and we are applying this layer to the input layer. This line effectively means that we are passing the input through a fully connected layer, thereby reducing the dimension to the self.encoding time. Moving on to the line 18, here in this line we are using the model class to define our encoder model. The model class takes in two main arguments, the input and output. Here the inputs to the model are the data that we pass into the input layer, and the outputs are the encoded data, the result of passing the input through the encoding dense layer, which leads us to the line 19. Here we are creating an input placeholder for our decoder. This will have the same shape as the output of our encoder, which is given by self.encoding time. And in the line 20, here now we are defining the decoding part of our auto encoder. This is another dense layer with the num nodes neurons, which should match the dimensions of the original input data. We are applying the sigmoid activation function here. The encoded input is passed through this layer. Moving on to the line 21, here similarly to the line 18, we are defining our decoder model using the model class. The inputs are the encoded data, the outputs are encoded data, and the outputs are the decoded data. Moving on to the line 23, here these lines combine the previously defined encoder and decoder into a full autoencoder, the self.encoder, which gets the input layer. This means that we are applying the encoder to our input and producing the encoded representation. Self.decoder is then used on the output, meaning we attempt to reconstruct the original input from the encoded representation. The result of this operation is stored in autoencoder output. Moving on to the line 24, here we are using the model class to define the full autoencoder model. The input to the model are the original data we pass into the input layer, and the outputs are the autoencoder output, the result of the passing the input through both encoder and decoder. Moving on to the line 26, here and this line defines a method compile autoencoder. This method will be used to configure the learning process before training model. Moving on to the line 27, here in this line we are calling the compile method on our autoencoder model. We are specifying Adam as the optimizer and binary cross entropy as a loss function. Adam is an optimization algorithm that can handle spiral gradients on noisy problems. Binary cross entropy is a loss function suitable for binary classification problems. And moving on to the line 29, here in this line we define the train autoencoder method. This function will be used to train our model. It takes self and adjacency matrix representing the input data. Epoch specifies the number of times that the learning algorithm will work through the entire training dataset, and the batch size indicates the number of samples to work through before updating the initial model parameter. Moving on to the line 30, the self.autoencoder.fit. Here we call the fit method on our autoencoder model, which trains the model for fixed number of epochs epochs, the first argument is the input data and the second argument is the target data. In this case, we are working with an autoencoder. The target is the same as input, and we also specify the epochs and batch size parameters, and we set the shuffle to true to shuffle the training data before each epoch. Moving on to the line 33 here. This line introduces a new method called encode. This method will be used to transform the input data, which is the adjacency matrix, into an encoded compressed form by using the train encoder. And the line 34 here, in this line we use the predict function on our trained encoder to transform the input data, the adjacency matrix, into the encoded representation. The result is stored in the encoded data variable. And the line 35 here, we return the encoded data from the encoded method. This represents the encoded version of the input adjacency matrix. Now we are defining an encoded method. This method is designed to perform the opposite of the encoded method. This takes an encoded data and tries to reconstruct the original input data using the trained decoder. And in the line 38 here, we use the predict method of our trained decoder to perform the encoded data back into its original form. The result is stored in the decoded data variable. And in the line 39 here, in this line we return the decoded data from the decoded method. This represents the reconstructed version of the original input data after it has been encoded and then decoded by the autoencoder. Moving on to the line 41, the class which is the class graph visualizer. As the name suggests, here we are defining a new class, and this class will be responsible for visualizing the original graph, the encoded graph, and the decoded graph. Moving on to the line 42, the initializer method. As you might have kind of guessed, this method initializes a method for the graph visualizer class. Pretty simple. Moving on to the line 43 here. In this line we are we initialize self.big to none. This attribute will be later used to store the figure object from Plotly, a popular data visualization library for the purpose of visualizing our graph. And in the line 45, this line introduces a new method called visualize graph. This method takes an input adjacency matrix of the original graph, the encoded data from the autoencoder, and the decoder data. This will create a visualization comprising of 3 pieces of data, which we are going to see in a minute, and after we run the code. And in the line 46, here we calculate the number of nodes in the original graph by taking the size of the first dimension of the adjacency matrix. In an adjacency matrix, the number of rows or columns correspond to the number of nodes in the graph. And moving on to the line 48, in this line we use the make subplots function from the plotly to create a subplot object with 1 row and 3 columns. Each column will contain a plot for the original graph, the encoded graph, and the decoded graph respectively. And the line 50 here, in this line we call a private method, which is the add edges. And the first underline indicates that this is a private call. And if you don't know programming, you have to know, object-oriented programming. You have to work with different libraries and encapsulation and all of these techniques. At least you have a good foundation to start the machine learning. You cannot learn machine learning learning without knowing, without a weak programming experience. And as I said, we in this line we call a private method add edges defined earlier of the graph visualizer class, passing in the adjacency matrix and specifying that the edges should be added to the first row and the first column of the subplot. This method will plot the edges of the original graph. Moving on to the line 51, here we call another private method, which is the add nodes, passing in a list of x and y coordinates of the nodes and specifying that the nodes should be added to the first row and the first column of the subplots. Note that the coordinates are generated using the range function with the num nodes as the argument, implying that the nodes are arranged in a line. Moving on to the line 54, here in this line, similar to the line 51, here we are adding nodes to the second column of the subplot. Here in the line 54, kind of similar to the line 51, but here we are adding nodes to the second column of the subplots with their corresponding with their coordinates being specified by the encoded data. Moving on to the line 56, similarly to the previous call to add edges, this line is used to add edges to the third column of the subplots representing the decoded graph. The edges are derived from the decoded data. Moving on to the line 57, just like the previous call to the add nodes, this line adds nodes to the third column of the subplots and their coordinates being specified by the decoded data. Moving on to the line 59, in this line the update layout function is called on the self.fig to set the height, width and the title text of the plots, and the line 60, this line is used to display the plots, and the show function is called on the self.fig, which opens a window with the visualized graph. Moving on to the line 62, this line defines a private method which is the add edges for the graph visualizer class. It is designed to add edges to a specific subplot based on the adjacency matrix of the graph. Moving on to the line 63, here in this line we use the np.where function to identify the position in the adjacency matrix where an edge exists, represented by 1. These options correspond to the pairs of nodes that are connected in the graph. And in the line 64, here we use the go.scatter function from the plotly to create a trace of edges. The x and y position of the edges are determined by the edges array from the previous line. Here we specify mod equal lines to indicate that we want to draw lines between the connected nodes. And the line 65 here, this line adds the edges traced to a specific subplot determined by the row and call. And in the line 67, which says def underscore add nodes, this line defines another private method for the graph visualizer class. This method will add nodes to a specific subplot with their x and y position provided as arguments. And in the line 68, here we use the go.scatter function again, but this time create a trace of the nodes, and the x and y position of the nodes are provided as arguments, and we specify the mod equal markers to represent the nodes as individual points. Moving on to the line 69, here this line adds the nodes traced to a specific subplot determined by the row and call. And the line 71 that says create sample dataset, this line introduces a function create sample dataset. This function is responsible for creating and returning a simple adjacency matrix that will be used for training training and testing the graph autoencoder. These lines from 72 to 76 indicates define a 2D NumPy array which represents our adjacency matrix. For the sample graph in the adjacency matrix, a value of 1 indicates that there is an edge connecting two nodes, and the value of 0 means there isn't. Moving on to the line 77, here this line returns the create adjacency matrix when the create sample data set function is called. So moving on to the line 79, which says def main. This line defines the main function that will orchestrate the entire process of creating graph autoencoder and training it and visualizing the result. Moving on to the line here, we call the previously defined create sample dataset function to get our adjacency matrix, which will be stored in the adjacency matrix variable. And in the line 83, which says graph autoencoder equals sign graph autoencoder class, which gets the encoding time 2. Here we instantiate the graph autoencoder class with an encoding time of 2. This means that the size of our encoded representation will be 2. The instance of the graph autoencoder class is served in the graph autoencoder variable. Moving on to the line 84. Here this line calls the built autoencoder method on our graph autoencoder object. It passes the number of nodes in our adjacency matrix received via adjacency matrix.shape we defined earlier to define the input and output dimension of our autoencoder. Moving on to the line 85. Here this line calls the compile autoencoder method on our graph autoencoder object. It will compile autoencoder model with the atom optimizer and binary cross entropy loss as defined in the method implementation. Moving on to the line 88. This line calls the train autoencoder method on our graph autoencoder object. It passes the adjacency matrix as both the input and the target data since we are training an autoencoder, and sets the number of training epochs to 100 and the batch size to 1. Moving on to the line 91. This line calls the encoded method on our graph autoencoder object and passes the adjacency matrix as an argument. This method takes the adjacency matrix and decodes it into a lower dimensional representation using the encoder part of our autoencoder. The resulting encoded data is stored in the encoded data variable. Moving on to the line 92. Here we call the decoded method on the graph autoencoder the autoencoder object and passes the encoded data as an argument. This method takes the encoded data and attempts to reconstruct the original adjacency matrix using the decoder part of our autoencoder. The reconstructed data is stored in the decoded data variable. And the line 95, the graph visualizer equals sign graph visualizer class, which we have right here. This line creates an instance of the graph visualizer class and assigns it to the variable graph visualizer. And the last line of our main function right here, the line 96. Here in this line we call the visualize graph method on our graph visualizer object and pass the adjacency matrix encoded data and the decoded data as an argument. This will create a figure with 3 subplots visualizing the original graph, the encoded data, and the decoded graph respectively. Moving on to the line 98 and 99. Here in the line 98, we check whether this script is the main module being run in the Python script or not. This script can be run directly or imported as a module in other script. If the script is being run directly, its name is set to the main, and this line ensures that the following code block is run only when the script is run directly. And the line 99, here this line calls the main function defined earlier. When the script is run directly, the main function is called to execute all operations where we define it, creating the graph autoencoder, computing it and training it on the adjacency matrix, encoding it back to the adjacency matrix, decoding it, encoding the adjacency matrix, decoding it back, and visualizing the original encoded and the decoded graph. So let's finally run the code. I'll fast forward the video. And here we have our graph autoencoder visualization. We have the original graph, the encoded graph, and the decoded graph. So after running the script, this window will open for you in Chrome, and this concludes the line-by-line explanation of the script and the process of writing a graph autoencoder script. I hope this video was informative to you and you learned something from it. If you have any question, put it down in a comment below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video where we are going to build a graph neural network from scratch in Python, and we are going to use the NumPy, Plotly, and Network X. So without further ado, let's dive into it. Our code base will create a graph neural network model, designs a simple dataset for testing, and performs training process and visualizes the graph structure using the power of Network X and Plotly library. And we will discuss each line of the code and how it contributes to the overall functionality of the graph neural network. So let's get started. In the line 1, we imported NumPy, which is a fundamental package for scientific computation in Python, and provides us with the support of array and matrices and numerous mathematical functions. Moving on to the line 2, here we import the Plotly, which is a powerful graphing library for making interactive plots. We specifically import the graph objects module, which includes the classes for all types of plots that we can create. And in the line 3, we import the Network X, which is a package that provides us with the capability to create, manipulate, and study the structure of complex networks. Moving on to the graph RNN class. Here in the line 5, we declare a new Python class named graph RNN. This class will encapsulate all functions necessary to build and train our graph recurrent neural network. Moving on to the line 6, here this line is a constructor method for the graph RNN class. It gets called when we create a new instance of the class. It takes an input number of nodes and the number of features per node, and the number of hidden units, and the number of output classes. Moving on to the line 7 up to line 10, here we initialize our class attributes using the parameters given in the constructor. This includes the number of nodes, the num nodes, and the number of node features, which is num underscore features, and the number of hidden unit, which is hidden underscore unit, and the number of output classes, which is num underscore classes. Moving on to the line 12, here we initialize the weight matrix w underscore h that maps the node features to the hidden state. The size of the matrix is the num features and the hidden units, and we initialize it with the random values from the standard normal distribution. Moving on to the line 13, similar to the previous line, we initialize the weight matrix W and Y that maps the hidden state to the output. The size of the matrix is hidden units and the num classes again, and it is also initialized with a random value from the standard normal distribution. Moving on to the line 15, def forward. This is a forward method for our graph RNN class. It takes the adjacency matrix, the node features as an input, and the adjacency matrix that represents the graph structure, where each entry adj underscore matrix, which has the I and j, it is 1 if there is an edge from the node I to the node j and 0 otherwise. Node features are characteristics or attributes of each node. Moving on to the line 16, here we initialize the hidden state of all nodes to 0. The size of this matrix is the number num node and the hidden units, again with the num nodes representing the number of nodes in the graph and the hidden units representing the hidden units in the RNN, as I explained before. Moving on to the line 17 and 18, here this is the main computation part of our forward pass. For each node we compute the hidden state as the sum of two terms, the product of the node features and the weight matrix, the W and H, and the product of the adjacency matrix for that node and that hidden state of all nodes. The adjacency matrix is used to incorporate information from the neighboring nodes into the hidden state. Moving on to the line 20, here we have the output. We compute the output by multiplying the hidden state matrix with the weight matrix W and Y. This will give us a matrix where each row corresponds to the output of each node. Moving on to the line 21, we want to return the output, obviously. Finally, the forward pass is complete and we return the computed output. This output can be used as prediction in a prediction task or compared with the actual value to compute the loss in a training task. Moving on to the line 23, here we have def train. This is a training method of the graph neural network class. It takes the adjacency matrix, the node features, target labels, a learning rate, and the number of epochs as an input. The labels represent the actual values or classes of each node. Moving on to the line 24, we have the hidden state. Similar to the forward method, we start by initializing the hidden state of all nodes to 0. This hidden state will be updated during the training process. And moving on to the line 25, we have a loop. Here we start a training loop which will run for the given number of epochs. An epoch is a complete pass through the entire dataset where the model learns from the learns and adjusts its internal parameters, the WH and WY, to minimize the loss. Moving on to the line 26, here this line invokes the forward method we explained earlier on the current state of the adjacency matrix and the node features. This action returns the predicted output y underscore paired for current state of the network. Note that these predictions are made based on the current weights in the network. Moving on to the line 27, here we have the loss. We calculate the mean squared error, MSE, the loss between the predicted output y underscore paired and the actual labels. The loss function measures the discrepancy between the predicted and the true values in the context of training a neural network, and our goal is to minimize the loss here. Moving on to the line 29, here we initialize the dw underscore h, which will hold the gradient of the loss with respect to the w and h. This gradient tells us how much the loss will change if we change the w underscore h slightly. It initialized as the zero matrix of the same shape as the w underscore h. Moving on to the line 30, here similarly we are initializing the dw underscore y, which will hold the gradient of the loss with the respect to w underscore y. It is also a zero matrix of the same shape as the w underscore y. Moving on to the line 32, here we began iterating over all nodes in the graph. For each node, we will compute and accumulate the gradients for the loss with the respect to the w underscore h and w underscore y. Moving on to the line 33, here we are computing the gradient of the loss with the respect to w and y for the t, which is the node, and adding it to the dw underscore y. The np.outer function computes the outer predict of two vectors. And in the line 34, here similarly we are computing the gradient of the loss with the respect to w and h for the t, which is the node, and adding it to the dw underscore h. We reshape the node features and adding a state to the column vectors so that we can use the np dot function to compute the outer product. Moving on to the line 36, here we perform the weight update for the t w underscore h using the gradient descent. The learning rate controls the size of the step we take in direction of the negative gradient. Moving on to the line 37, similarly we are updating the weight matrix the w underscore y using the gradient dw underscore y and the learning rate. Moving on to the line 39, if epoch, here this line checks if the current epoch is the multiple of 10. This is a common way to display the training process periodically rather than every single epoch, which could be overwhelming and less informative. Moving on to the line 40, here the process of the training is printed to the console. It displays the current epoch number, the number of total epochs, and the current value of the loss. This output allows us to monitor the training process and verify that the loss is decreasing as expected. So let's move on to the class dataset. Here we are defining a new class called dataset. This class is used to create and manage our data for this script, and in a more complex application, this class might handle the loading and pre-processing of a large dataset, but here simply generates a small fixed example. Moving on to the line 43, here we define a method in the dataset class called createSample, and this method proposes to guarantee a sample graph with the predetermined attributes. Moving on to the line 41, 44 up to 47, here we define an adjacency matrix of the graph. This matrix describes the connection between the different nodes in the graph. If the ADG underscore matrix is 1, it means that there is a link from the node I to the node J. A0 means that there is no link. Moving on to node features in the line 49 up to line 52, here we define a feature of each node in the graph. Each row correspond to the node and each column correspond to the feature. In this case we have 2 features per node. Moving on to the line 54 up to line 57, we define the labels for our nodes here. These are the ground truth values for our target outputs that we will use to train our graph RNN. In a classification problem, this could represent the class labels. And finally, in the line 59, the createSample function returns the adjacency matrix, the node features, and the labels. These will be used as an input for our graph RNN. So let's move on to the graph visualizer class This again is the easy one. And this line creates a new class called Graph Visualizer. This class is responsible for visualizing our graph using the adjacency matrix. The line 62, inside of our Graph Visualizer class, we define a method called Visualize Graph that takes the adjacency matrix of our graph as an input. The purpose of this function is to create visual representation of our graph. Moving on to the line 63, here we use the Network X library, which is a powerful tool for manipulating and analyzing complex networks. This function, which is the nx.fromNumPy array, creates a new network X graph with J from the adjacency matrix. And moving on to the line 64 that says pose, this line generates the layout for our nodes in the visualization. The spring layout function is one of the several methods of network X that provides a computing node position. It uses a force directed algorithm which treats the edge like a spring holding nodes close while treating nodes as replicating objects, resulting in a visually pleasing symmetrical layout. Moving on to the line 65 up to the line 70, here these lines create a scatter trace for the edges of our graph. The scatter is a type of plotly object that we are using to represent our edges. We initialize the X and Y arrays as an empty because we will be filling them up in a loop. This line sets the static of our edges, including their width and color. Moving on to the line 72, this line begins the loop over each edge in the graph. Inside this loop, we will be executing the coordinates of the edge and adding them to our edge trace. The line 73 up to line 76, here we extract the position of the two nodes that the edge connects. Each position is a 2D corresponding, so it is represented by a pair of values x and y, and we add the x and y coordinates of the two nodes to the edge trace and x and y arrays with a non-element in between. The none creates a break in the line, as the plotly will not draw a line segment between the coordinates and the none. This allows us to represent multiple disconnected line segments within a singular scatter trace. Moving on to the line 78. So let's see them full. The line 78 up to line 96 up to right here. Here we are creating another scatter object for the nodes of the graph. We specify that we want to display markers, the dots at the location of each node, which we are going to see after running the code, and the text, which is the label next to each node. And we will also show additional information when hovering over the node, and we specify that when we say hover info text right here, the color scale parameter is set to the YLGNBU, a built-in yellow, green, blue color scale provided by the plotly, and reverse scale is set to true, which means that we want to flip the order of the colors in our color scale. The color is an empty list of nodes. The size parameter sets the size of the markers, which is the nodes, and the line width sets the width of the border around the markers. The color bar parameter adds a color bar to our graph with the specified properties. And moving on to the line 98 right here. On this line, it starts a loop node over our graph. For each node, we will extract the coordinates and add them to our node trace. And in the line 99 up to line 101, we extract the position of each node and add it to the node trace x and y list. These coordinates will be used by plotly to replace the nodes that the current position, used by plotly to place the nodes at the the correct position on the plot. Moving on to the line 103 up to the line 111, here these lines create a figure object that contains our data and layout information. The data argument takes a list of our traces, the edge trace and the node trace. The layout argument specifies a layout object which has several styling parameters, including the feature title, the font size of the title, and the visibility of the legend, the hover mode, the margin around the plot, and the properties of the x-axis and y-axis. We will disable the axis grades, 0 lines, and the thick labels for a cleaner plot, since the exact numeric coordinates are not important in this context. Moving on to the line 113, this line displays the plotly figure we have created before. When this line of code is executed, it will create a new window of our tab displaying the graph we want to construct and style. Moving on to the line 115, this line marks the beginning of the main function. This function will integrate all previous components, running the entire process from creating the dataset, visualizing the graph, and training the RNN model, and presenting the result. The line 116 up to line 118, here we instantiate the dataset and the graph visualizer class. Then we use the create sample method of the dataset instance to generate our adjacency matrix, node features, and labels. Moving on to the line 120 up to line 121, right here, the GNN. In these lines we create and initialize our graph RNN model. We pass the number of nodes which we get from the shape of the adjacency matrix, the number of features from the shape of the node features matrix, the number of hidden units, we chose 32 in this example, and the number of classes which we will get from the shape of the labels matrix. Moving on to the line 123 and line 124. Here we are defining two important hyperparameters for our training process: the learning rate and the number of epochs. The learning rate controls the step size at each iteration while moving towards a minimum of a loss function. In this case we set it to 1, and the number of epochs, it is the number of complete passes through the training dataset, so we set it to 100. And in the line 126, the GNN.train, this line of the code starts the training process of our GNN model. We pass in our adjacency matrix, node features, labels, and the learning rate, and the number of epochs to train the method of the graph RNN instance. Moving on to the line 127, after training our graph RNN model, we make prediction, and this is done by running the forward pass method of the graph RNN instance, passing our adjacency matrix and the node features argument. The forward function computes the output of the model using the latest updated weights. The output is the estimate labels, the predictions for the nodes. The output is the estimated labels, which is the prediction. The output is the estimated labels for the nodes. Moving on to the line 128, MSE. As the name suggests, this line calculates the mean squared error of our model prediction. MSE is a popular matrix used to evaluate the performance of the regression model. It is calculated by subtracting the true labels from our predicted labels, the X, the Y predict labels, squaring the differences to make them positive, which is the part that we say Y predict minus labels multiplied by 2 to the power of 2, not the multiplied by 2, and then taking the mean of these square differences and then taking the mean of these square differences. Moving on to the line 129 up to line 130, these two lines are simply printing out the predicted output of our GNN model and then the mean square error of these predictions, and this is very useful for us to understand how well our model is performing. Moving on to the line 131, here we call the visualize graph method on our graph visualizer instance, passing our adjacency matrix as an argument. This line will generate a graphical representation of our graph as defined earlier in the visualize graph method. And the line 133, if you're programming, you definitely know this one. This line is a special line used in Python script when the Python interpreter needs to read the source file. First sets a few special variables. The name is one of them. When the script is being run directly, the interpreter sets the name variable to have a value main. So the code inside of this if condition that we have here will run only if the script is being run directly. And in the line 134, this line calls the main function, which kicks off everything we defined so far when we run the script. The code starts by calling the main function and execute everything inside of the main function and show us a result. So let's execute the code and see what we are going to get. And as you can see, it opened a window for us, shows us the result. So it's a very simple representation, and this script implements a simple version of graph recurrent neural network model for learning from the graph structured data. In summary, this script is a complete flow of data generation, the model training and prediction, and visualizing in a context of graph RNN. I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video about implementing and training a graph attention network in PyTorch. GATs are a neural network that operates on a graph data structure. They are particularly powerful because they are capable of extracting complex patterns from the graph structure while paying more attention to the most influential nodes. Our objective is to construct a GAT that can learn node representation from a simple graph and then perform a node classification. So let's get started. In the line 1 up to line 5, here we import the necessary libraries. In the line 1, we start by importing the network X, a Python package that provides a tool for creating, manipulating, and studying the structure and function of our complex network. Network X will be used in the script to build our graph object from a set of nodes and edges. In the second line, we import the PyTorch, which is a powerful deep learning framework that provides a tensor, computation, and deep neural network. In the line 3, import torch.nn as NN. Here we import the NN module from the PyTorch. The NN module provides a set of classes for defining and training our neural network. Here in line 4, we import the torch.nn.functional as f, which is a function that contains a style and interface for a lot of neural network operations, and we typically import it as an alias of f, and we will use this for our activation function and other operations that don't have parameters. Moving on to the line 5, here we import the polygraph objects as Go. The polygraph object is a high-level interface to Plotly graphing library, which allows us to create richly interactive and stylized graphs. We will use it to visualize our training loss and the final node representation. And from line 7 up to line 10, here we have our global variables, the nodes, edges, and labels, which will be used to create our graph label and our nodes. This is a simple graph with 3 nodes, 2 edges, and each node have a unique label. Moving on to the line 12, we have our first class in the code, which is named graph. This class will hold the functionality to create our graph, gets its adjacency matrix, and convert the node labels into tensors. The adjacency matrix of the graph is a square matrix where the entry in the ith row and the gth column, which is equal to the number of edges between the vertices I and j. And moving on to the line 13, here we have our first function in the graph class. The initializer of the graph class takes 2 parameters, the nodes and edges. The node parameter is a list of all nodes in the graph, and the edges parameter is a list of tuples where each tuple is a pair of nodes that form an edge. Moving on to the line 14, here we have the self.graph, an initializer that we call the create graph method defined below to create our graph using the provided nodes and edges. Moving on to the line 16, here we define a method create graph that will create the graph and takes the nodes and edges as parameters. We have g equals sign nx.graph. Here we instantiate a new empty undirected graph objects from the node network x, and in the line 18 g.add nodes from. Here this line adds multiple nodes to the graph at once from the provided list of nodes. Each node is an entry in the graph, and in the line 19 here we add multiple edges to the graph at once from the provided list of edges, and each edge is a connection between 2 nodes in the graph. And in the line 20 finally we return the g after creating the graph, so here we return it. Moving on to the line 22, here we define the method get adjacency matrix to get the adjacency matrix of the graph. The adjacency matrix is a way of representing a graph as a matrix in which the cells indicate whether there is an edge or not between the vertices. Moving on to the line 23, this function was very short, and we use the network x function adjacency matrix to get the adjacency matrix of the graph. The adjacency matrix is a sequence of square matrices where the I row and the j column is filled with 1 if there is an edge from the node I to the node j, otherwise it is filled with 0. The toDense function is used to convert this Aspire matrix representation into a dense NumPy matrix. Moving on to the line 25, here we define a method get labels that takes a list of labels and converts it into the PyTorch tensor of the type torch.long. This tensor will be used as our target labels for training the network. Moving on to the line 26, here we return and kind of convert the list of labels into a PyTorch tensor with the data type torch.long. And moving on to the line 28, here we have the class GAT layer. So let's fill the screen with it. We define the GAT layer, we can say class, which inherits from the PyTorch NN.module. This class will define a layer of our graph attention network. And the line 29, here we use initializer of the GAT layer. We specify the dimensionality of the input and output, the dropout layer, and the parameter alpha for the leaky ReLU activation function. Moving on to the line 30, here we call the superclass initializer. This is necessary for the PyTorch intervals to work correctly. And the line 31, here we define a linear transformation without biases as per the graph attention paper. The linear module applies a linear transformation to the incoming data y equal sine x multiplied by w caret sine t. In our case, the w is a weight of matrix which transform the input features x into a higher level representation. Moving on to the line 32, here we define the attention weights which will be learned during the training. These weights are used to compute the coefficiencies that weight the influence of each neighbor node in the graph. We initialize our attention weight in the line 33 using the Javier uniform initialization, which is a common practice to set the initial weights. This can help prevent the model from the getting stuck in the initial stages of the training. The line 34, here we store the dropout layer which will be used later. The dropout is the regularization technique where randomly selected neurons are ignored during the training, helping to prevent overfitting. The line 35, here we store the alpha parameter for the leaky ReLU activation function which will be used in the attention mechanism. And the def forward in the line 37, here we define the forward method for our GAT layer which will be called during the forward pass of our network. It takes the feature of matrix X and adjacency matrix A as an input. The line 38, here we apply the linear transformation to the input features. And the line 39, here we then compute the preliminary attention value before softmax by multiplying our transform features by our attention weights. The line 40, here we create a very large negative number which will act as a mask for our non-adjacent nodes. Moving on to the line 41, here we apply our mask to our preliminary attention value if nodes are adjacent, indicating by the entries in our adjacency matrix A. We will keep the attention values, and otherwise we will replace them with our very large negative number. And in the line 42, here we apply the leaky ReLU activation function with the negative scope alpha to the attention values, and then normalize these values across each row using the softmax. This ensures that the attention value sum to 1 for each node neighborhood, allowing these values to be interpreted as probabilities. And the line 43, here we apply the dropout to our activation values. This randomly sets some attention values to 0 during the training, which can help us to prevent overfitting. Moving on to the line 44, here we finally compute the dropout feature as a weighted sum of the input features, where the weights are the attention values. And the line 45, it's pretty simple. We return the h prime. The output of the forward pass of the GAT layer is returned here. And the line 47, here we define the GAT class, which inherits from the PyTorch NN.module. This class will define the graph attention network for us. And the line 48, here we in the initializer of the GAT, we specify the dimensionality of the output, the hidden layer, and the dropout rate, and the parameter alpha for leaky ReLU activation function. And moving on to the line 49, here we call the superclass class initializer, which is a necessary part for our PyTorch internals to work correctly. And moving on to the line 50 up to 53, here we have these self.layers. Here we create a list of GAT layers using the NN.module list. This is a list which will be a sequence of 2 GAT layers, first transforming the input data to a hidden representation, and the second transformation, which is the hidden representation, to the output data. Moving on to the line 54, here we define our additional linear transformation layer that will be applied after the GAT layers. And the line 56, def forward, here we define the forward method for our GAT, which will be called during the forward pass of our network. It takes the feature matrix X and the adjacency matrix A as the input. And the line 57 here is h equals sign x. We initialize our hidden state h with the input feature x. And the line 58 and 59, here we have the for each layer in our GAT, we pass the hidden state and the adjacency matrix. The output of each layer becomes a new hidden state for the next layer. And the line 60, here we apply the final linear transformation to our hidden state to get the output of the GAT. And in the line 61, here we apply the softmax function to our output to normalize it into a probability distribution, and then apply the logarithm. This is commonly done in the multi-classification problems to prepare the network output to be compared to the true class label in the loss function. In the line 63, here we define a trainer class to handle the training of our graph attention network. And in the line 64, here the trainer is initialized with the model optimizer and certain loss function, criterion loss function. And in the line 65, here we save the model into a trainer object. And the line 66, here we save the optimizer into a trainer object. The optimizer is an algorithm that adjusts the model parameters to minimize the loss function. And the line 67, here the self.criterion, we save the loss function into the trainer object. This will be used to qualify how far the model predictions are from the true values. Moving on to the line 68, here we initialize an empty list to record the lost values at each epoch. And in the line 70, we have the train function, which takes in the feature matrix, adjacency matrix, true labels, and the number of epochs as an input. And the line 71, here we start a training loop that will be iterate over the number of epochs provided. And the line 72, self.optimizer.0 grad, here before the backward pass we use the optimizer to 0. All of the gradients for the variables it will be updated, which are the learnable weights of the model. This prevents gradients from the accumulation across multiple backward passes. And in the line 73, here we have the logits. We perform the forward pass of our model, giving our raw output scores. And the line 74, here we compute the loss value for our current epoch by computing the logits to the true labels. Moving on to the line 75, here we perform the backward pass, which is our back propagation, to compute the gradients of our loss with the respected to the model parameters. In the line 76 self.optimizer.step, here we update the model parameter by performing a single optimization step, and in the line 77 here we record the current lost value for the later visualization, and in the line 78 up to 79 here we have the print epoch and loss. Here every 10 epoch we print the output of the epoch number and the lost value, and in the line 81 here we define a function plot losses that will be used to visualize how our loss changes over the time, which can give us an insight about the learning process. And in the line 82 here we create a new plotly graph figure, and in the line 83 here we add the scatter plot to the figure that plots our recorded losses against the epoch number. The mode is set to the lines so that line will be drawn and connects our points. And in the line 84 here we update the layout of our figure to set it to the title of the graph and the labels of our the x and y axes. In the line 85 here we have the fig.show, which it's pretty simple and shows for us and displays the figure that we want. Here we define a GetApp class. This class will serve as the main application that will bring together the graph data, the get model and the trainer for us. And in the line 88 the GetApp class is initialized with the nodes and edges and labels, the dimensionality of the input, hidden layer, and the output, the number of heads and dropout rate and the learning rate are set here. And the line 89 here we create a graph instance with the given nodes and edges, and in the line 90 here we convert the provided labels to a tensor with the graph get labels method, and the line 91 up to line 96 I guess, yes, the line 91 up to line 96 here, these are pretty simple. We store all provided parameters for the later use, and in the line 97 we initialize the get model. Moving on to the line 98 here we create an Atom optimizer which will be used to update the model parameters during the training. The optimizer is a given parameter of the model and the learning rate. And the line 100 here that says define initialize model, which gets self as a parameter. We define a helper method to initialize our get model. And the line 101 here we have return a new get instance with the previously set parameters. And the line 103 here we define a method that runs the train get model on our data and then visualizes their learning process and the final node representation. And the line 105 here we instantiate a trainer object, providing it with our model optimizer and a cross entropy loss function. The cross entropy loss function is commonly used is a commonly used loss function for classification tasks. And the line 106 here we extract the adjacency matrix of our graph using our previously defined method, which is get adjacency matrix, and convert it to a PyTorch tensor and ensure that it is of a float type. The line 107 here we call the train method on the trainer, which will train our model for 100 epoch. We pass a figure matrix of ones as we are not considering any particular features of nodes, and the adjacency matrix and the true labels are passed as ones. And in the line 110 after training we plot the losses recorded during the training process to visualize how the model learned over time. Moving on to the line 113 we enter a context where gradient calculations are turned off. This is because we are going to make predictions with the model and we don't want these operations to be tracked in the computation graph. Moving on to the line 14, here we pass the feature and adjacency matrices to the model to get the output node representation and convert the tensor to a NumPy array. And in the line 16, here we create a new plotly figure, and the line 117 up to line 119, here we iterate over all nodes in the graph, adding a scatter plot to figure for each node. The scatter plot is set to the markers node, marking the position of each node into a two-dimensional space of the first two dimension of the node representations. We set the size of the marker and the label to a point with its class. And the line 120, here we set the title of the graph and the labels of x and y axes. And the line 121, here we display the figure showing the final node representation learned by the GAT model. And the line 124, here we return here to run the script we instantiate the GAT app class with our nodes, edges and labels. And finally in the line 125, we call the return method on the GAT app instance, which triggers the whole process of the training the model and visualizing the result. So let's run the code and finally see what we are going to get. So I fast forward the video, our operation is done, and let's see the result. It opened a window for us in the Chrome. Sometimes this has only the trace 2, sometimes there is the trace 0, sometimes the 3 of them are present in the graph. So it really depends on the calculations. And we have the GAT training loss here as a linear as a line graph. So both of them are the GAT node representation and the GAT training loss are visualized. And in this script we demonstrate how to implement and train the graph attention network in PyTorch, which is a powerful tool for dealing with graph structured data. This script started by defining the basic building block for handling graph data, the graph class, which is responsible for creating the graph and generating adjacency and the labels. Next we had a GAT layer class, which represents a single layer of the graph attention network. This class handles the weight initialization and the forward propagation for a single layer, including the computation of the attention coefficients. The GAT class represents the overall network architecture and consists of multiple GAT layers stacked together. And finally we connected the layers. It is which is responsible for propagating the input through the layers and generating the final output. The trainer class manages the training process of the model, taking care of the gradient computation, backpropagation, optimization step, while also tracking and visualizing the losses during the training process. Moving on to our last part of the code, which is the class GAT app. Here the GAT app class integrates all above components into an application that creates a graph, initializes the model and performs a training process, and visualizes the learned node representation. And finally, in conclusion, this script demonstrated the practical implementation of a graph attention network from creation of the graph data structure through the process of defining and training the network to visualizing the result. As such, it serves a useful tutorial for understanding the inner workings of the graph attention networks and how they can be implemented and trained using the PyTorch. So I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video. In this video we are going to take a look at graph generative model, which is a type of computer algorithm designed to create new graph. In short, it's a way to automatically create new examples of graph based on patterns learned from the existing ones. And in this video we are going to create a graph generative model from scratch. So let's get us started. In the line 1 we import the Torch, which is a library for tensor computations and gradient-based optimization. In the second line, we import torch.nn.functional as an alias of f, which provides functions like activation functions that we need in this script. And in the line 3, we import torch_geometric.nn, and we are importing GCN conv, VGAE, and PyGVGAE. The GCN conv is for graph convolutional operations, and the VGAE is for building a variational graph autoencoder from the PyTorch geometric library. And in the line 4 we import torch geometric.utils, and we import dense to sparse, which is a utility function to convert dense matrices like adjacency matrix into a spire format, which is efficient for representing graphs. And in the line 5 we import matplotlib.pyplot as a PLT for short. Here this library is going to be useful for us for visualization of our data and our graph. And finally in the line 6 we import networkx as an alias of nx, which is designed for creating, manipulating, and a study of complex networks and nodes, which we need in this scenario that we have. Here we have an encoder class in the line 8 up 13. These lines define a custom encoder class for our VGAE, and it is essential for learning representations of our graph nodes. In the line 8 we declare an encoder class that inherits from the torch.nn.module, which is a PyTorch based class for all neural network modules. And in the line 9 we have def init. Here we define an initialization function of the encoder class, which sets up the encoder with necessary parameters like input, output, channel sizes. We have a super function, which is an initializer of the base class torch.nn.module to properly initialize our encoder instance. And in the line 11 we have self.base.conv, which initializes a graph convolutional layer as a base convolver of the encoder, specifying the size of input and output features. And in the line 12 we set up another graph convolutional layer to produce the mean or mu of the latent variables. In the line 13 we initialize a graph convolutional layer for computing the log standard devision, log std, of the latent variables, a part of the reparameterization trick in the variational autoencoders. And in the line 15 to 17 we define a forward path of the encoder producing input features and age indices and produce latent variables. In the line 15 specifically we declare a forward method which is automatically called by PyTorch during the model forward path. And in the line 16 we apply the base convolutional layer followed by the ReLU activation function on the input features x and the edge index that we have. And in the line 17 we return the mean and log standard devision of the latent variables by applying the respective convolutional layers on the transformed features x. And in the line 19 up to 21 we set up the VGAE model by integrating the custom encoder that we want. So specifically in the line 19 we define the VGAE model class extending PyTorch geometric. VGAE class utilizes its variational graph autoencoder functionalities, and in the line 20 we initialize a function for VGAE model specifying the encoder with the input and output channels. And in the line 21 here we have a super function that initializes the VGA with the custom encoder and no specific decoder using the default provided functionalities by PyTorch geometric. And in the line 23 up to 28 we have our graph dataset container. Here we want to define a simple class to hold the graph data including the node features, edges, labels and training mask. In the line 23 here we have a class graph dataset which declares a class to encapsulate the graph data set, making it easier for us to manage and pass around the data components. And in the line 24 the initializer for the graph dataset task, and here the line 24 obviously is an initializer for a graph data set task, the node features X, the edge index, node labels and a mask to indicate which nodes would be used for training. And in the line 25 here we want to store the node features matrix in the instance variable X, and the line 26 stores the edge index which indicates the start and end nodes of each edge in the graph. And here in the line 27 self.y equal y stores the labels of the nodes which could be used for supervised learning task that we might want to have. And in the line 28 here we store the training mask indicating which nodes are to be considered during the training. And we have the training function for VGAE which is from 30 up to line 37. Here in the line 30 we first define a train VGA function that declares the training function with the parameters for model, and the data is an instance of the graph dataset, and the optimizer is used for the training. And in the line 31 model.train, here we put the model into training mode, affecting certain layers like dropout which behave differently during the training versus the testing. And in the line 32 we want to reset the gradients of all model parameters before the forward path, and which is necessary for correct gradient accumulation that we want, and it is necessary. And in the line 33 here we want to encode the graph node features and edge index to the latent space representations, which is Z if you did not understand. And in the line 34 we want to compute the total loss as the sum of the reconstruction loss, or basically how well the model can reconstruct the graph, and the KL divergence loss, which is a regularization term, computes the total loss as the sum of the reconstruction loss, basically how well the model can reconstruct the graph. And the KL divergence loss, which is a regularization term encouraging the latent space distribution to approximate a prior distribution scaled by the inverse of the number of nodes. Moving on to the line 35, loss.backward here performs the backward pass to compute the gradients of the loss with respect to the model parameters. And in the line 36, optimizer.step, here we update the model parameters based on the gradients computed during the backward. And finally in the line 37 we return the loss value as a Python float. And here from line 39 up to 45 we have the visualizing of our graph. Here we provide utility function to visualize the graph structure using the network X and matplotlib. In the line 39 we define a function for graph visualization giving an edge index and an optional title. In the line 40 we create an empty undirected graph using the network network X. In the line 41, here we transpose the edge index tensor and convert it into a list of edge tuples. And in the line 42, here we add the edges to the network X graph based on the edge list. And in the line 43, we draw a graph with nodes and labels and a specified node color. In the line 44, we set the title of our plot, and in the line 45, we want to display the plot. And moving on to the main function, here from the line 47 up to 75, we define a main function where the entire process of graph generation using VGAE is orchestrated, and from the data preparation to the training and visualization, all of them are being executed in this function. And in the line 47, we declared our main function, and here's when the execution begins in our code. And here in the line 48, after that we create an identity matrix of the size of 4 by 4 as the node features, where each node is represented by a unique one-hot encoded vector. And in the line 49, we define a graph connectivity in the COO format, a list which is a list of start and end nodes for each edge, representing for us a simple graph structure. And in the line 50, we specify the node labels, which could be used for graph classification or other supervised tasks, though it's not directly used in the VGA training here, so keep that in mind. And in the line 51, we define a training mask where all nodes are marked as true, indicating they are all to be included in the training process. And in the line 52, here we want to instantiate the graph data set class with the previously defined features, the edge index, labels, and the training mask. And in the line 54, here we determine the number of input channels features per node, which is delivered from the size of the node features matrix X that we had. And in the line 55, we set the number of output channels during the dimensionality of the latent space for the VGAE that we have. And in the line 56, here we initialize a VGAE model with the specified number of input and output channels. And in the line 57, we set up the optimizer for training the VGAE using the Adam algorithm with a learning rate of 0.01. And here in these lines from 59 up to 62, we have a training loop that runs for 200 epochs, printing the loss every 10 epochs. And in the line 59, for epoch in the range of 200, here, as I told you, we start the loop to train the model for 200 epochs. And in the line 60, here we call the train VGAE function to perform a single training step and return the loss. And in the line 61, here we check if the current epoch number is divisible by 10 to print the loss periodically. And in the line 62, we print the current epoch and the training loss. And here in the line 64, we visualize the original graph structure using the visualize graph function. And in the line 66 up to line 73, here we visualize the graph generated by the VGAE model. In the line 66, we switch the model to evaluation mode, affecting layers like dropout. And in the line 67 up to 71, here we encode the graph and we generate a new adjacency matrix from the latent space threshold. The adjacency matrix that we have creates a binary graph and extract the edge index for the generated graph. And here finally in the line 73 we visualize the generated graph, and the line 75 and 76 here checks if the script is being run directly by the main program and calls the main function, and this is where our code first gets executed. So let's run the code and see the final result. And as you can see, we have our 200 epochs and the loss are being printed to the terminal. So this is our generated graph. We have another one, here's another one, and this script demonstrated for us a complete workflow for generating a graph using variational graph autoencoder or VGAE, from initializing the model and data to the training the model and visualizing the original generated graph. So I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video. Hello and welcome to this video. In this video we want to learn about fraud detection with graph anomaly detection technique, which is a crucial part of today's financial digital realm. Financial institutions need a robust and real-time system to detect and prevent fraudulent transactions. Graph anomaly detection is a sophisticated technique that identifies unusual patterns that do not conform to expected behavior that we want, such as fraudulent transactions in a network, which usually is done by a website payment gateway. And in this script we are building a basic fraud detection system using graph anomaly detection from absolute scratch. This script is divided into several parts. First, we want to connect to a graph database, which is in this case is Neo4j, and we are establishing a connection to Neo4j graph database to fetch transaction data. So if we go to the Neo4j database, as you can see we are using the basic example of fraud detection database, and Neo4j itself provided this database in their software. And if we open it and go through the browser of Neo4j, here as you can see we have different clients. There are thousands of clients that we have, and if we click on them you can see they have different edges, connections to one another, and this is a very useful database that we can use. And as you can see right now, let me show you in the right side of the screen, it says ID, amount, fraud, global step, ID, step, and TS. These are a very useful information that we can use in our fraud detection mechanism, and it tells us the status of fraud currently, if it is true or if it is false. So let's go through the script, and here in the script, after we connect to the Neo4j, we have a class called data processor, then we have a model builder, we have a model evaluator, and we have our anomaly finder class, and we have a bubble graph class which is used for visualization, and finally we have a main function that executes our code. And this is a very basic script, so let's go through it. You have to have PyTorch installed, also you have to install PyTorch geometric, and you need to install Plotly, Scalearn, and you can install all of them using pip install, for example torch. And if you're watching this video you have to know this type of topics, because this is an advanced topic that we are taking a look at, and this is not a beginner's code. So let's go through the libraries first, and let me explain to you each and every library that we imported. In the line 1 we imported the PyTorch, which is a popular open source machine learning library used for machine learning tasks, deep learning, and is a foundation for building a neural network model in this script. Secondly, we import the torch.nn functional as f. This line imports the functional module from the PyTorch NN package, which is commonly referred to as f. This module usually contains loss function and activation functions that we want to use in our machine learning script. And in the line 3 we import torch geometrics.data, and this line imports the data class from PyTorch geometrics as an extension library for PyTorch. Data is used to represent graph, including the node features, edge indices, and labels. And in the line 4 we are using torch geometrics.nn, and we are importing it, and we are specifically importing the GCN conv from it, which is a convolutional network from PyTorch geometrics. And in line 5 we are importing the graph database which we want to get our data from. And in the line 6, this line imports the graph objects module, commonly referred to as Go, which contains all graphical objects to create a wide variety of visualization type. In the line 7 we are importing the F1 score, the precision score, and recall score from scikit-learn, which is a popular machine learning library in Python, and I will explain to you later what F1 score is, recall score, and precision score in detail. And in the line 8 we are importing the logging. This line is a Python built-in module which is used to output the log messages from the application. And in the line 10 up to 13 we have our database connection and threshold configuration, and these lines define the constant used to connect to Neo4j database and set a threshold for identifying high value transactions. In this case we want to get every transaction that is above 1 million. And if we go through the database, here we can see the user list. We have Neo4j itself, which is an admin, and we have our JDB, which is an alias for graph database, and FAD is for fraud anomaly detection. And you can add the user. If you don't know, you go to server user add, and right here you add a user. This is pretty simple, and let's continue with our script. In the line 15, and this line initializes the logging system for this Python program. The basic config function from the logging module is used to configure the logging. In this case the log level is set to info, which means that the logger will handle all messages with the security level of info or higher. The messages with the survey levels of debug will be ignored. This is useful for getting the informational messages such as confirming that the system is running as expected, and for troubleshooting or diagnostic issues. And in the line 17, this line defines a new class named Neo4j connector. This class is responsible for handling the connection to Neo4j. It provides a method to connect to the database, execute the cipher queries of Neo4j, and closes the connection. Also in the line 18, here this line defines the init method for the Neo4j connector class. The init method is a spiral method in Python known as the constructor, which is called when an object is instantiated from the class. And in this case the constructor takes three parameters: the URI, the user, and the password, which are used to connect to the Neo4j database. Moving on to the line 19, and in the line 19, this line is inside the init method of the Node4j connector class. It assigns the value of the URI parameter to the instance variable of self.uri. This URI is the connection string needed to connect the Neo4j database, typically in the form of bullet, hostname, and port. Moving on to the line 20, this line assigns the value of the user parameter to instance variable self.user. In the Neo4j class, the user required to authenticate with database. Moving on to the line 21, this line assigns the value of the password parameter to the instance variable self.password. In the Neo4j connector class, the password parameter represents the password required to authenticate with the Neo4j database. And in the line 22, self.driver equals sign none. This line initializes an instance variable named self.driver self.driver with the value none in the Neo4j connector class, the driver object will later be used to manage the connection to the Neo4j database. Initially, it is set to none to indicate that there is no active connection. Moving on to the line 24, this line defines a method named connect within the Neo4j connector class. The purpose of this method is to establish a connection with the Neo4j graph database. Once called, the method will attempt to create a new connection, a driver in the Neo4j terms, to the database using the URI, user, and the password that we stored in the instance when it was initialized. And in the line 25, this line begins a try block. The try block is used to enclose a section of the code where an exception, usually an error at the runtime, might occur. The purpose of this block is to catch exceptions that may be thrown when attempting to connect to the Neo4j database, allowing the program to handle them gracefully instead of crashing. And in the line 26, self.driver, this line attempts to create a new connection to the Neo4j database. It calls a driver method of the graph database class, which was imported from the Neo4j module with the URI, user, and password instance variable as an argument. If successful, this method will return a driver object which is stored in the self.driver instance variable. The auth argument is a tuple connecting the user and password that where we pass them to the init method when the Neo4j connector object was created. And in the line 27, here this line begins the except block that catches the exception of the type exception or any subclass thereof, which are assigned to a variable named e. If an exception is thrown inside the try block, for example, if the connection to database fails, the code within this exception block will be executed. Moving on to the line 28, this line is inside the except block. If an exception occurs, as I told you, attempting to connect to the database and fails, this error message will be shown to the client failed to create the driver, and it helps in debugging the code. Moving on to the line 29, self.driver equals none. This line, it is also inside the exception block. If an exception occurs, this line sets the driver to the instance variable of none. And in the line 31, def close, which gets self as a parameter, this line defines a method named close within the Neo4j connector class. The purpose of this method is to close the connection to the Neo4j graph database when it's no longer needed. And in the line 32, here this line is also inside the close method function, and the condition checks if the self.driver is not set to none and if there is an active connection to the Neo4j database, and if the self.driver is none, it means that there is no active connection and thereby closes the connection. And in the line 33, self.driver.close, this line, it is inside the if block, and then it is inside the close function, and as you can kind of guess, it will close the connection by closing the self.driver object. Moving on to our next function, which is execute cipher query. This line defines a method named execute cipher query within the Neo4j connector class. This method takes one parameter, the query, which is expected to be a string containing the cipher query. The cipher is a Neo4j query language for querying the graph database. The purpose of this method is to execute the given cipher query on the connected Neo4j database and return the results. So in the line 36, we are initializing a context manager block within the Neo4j session object. The session method is called when is called on the self.driver object, which represents the connection to the Neo4j database. To create a new session, this session object is represented by the variable session This is used to manage the interaction with the Neo4j database with keyword as. The statement ensures that the session is properly closed after the block of code is executed, regardless of whether an error occurs. And in the line 37, we have the result equals sign session.run, and inside of the run method there is query. This line is inside of the context of Neo4j session and executes the cipher query that was passed as an argument to the execute cipher query method. The run method of the session object takes the cipher query, which is a string, as an argument and sends it to the Neo4j database for execution. The result of the cipher query is stored in the variable result, and in the line 38, after the cipher query has been executed and the result object has been populated with the data returned by the Neo4j database, this line converts the result object to a Python list and returns that list from the executed cipher query method. Each element of this list is a record that presents a row of the query result. This allows caller of execute cipher query to easily process the result of the cipher query. And in line 40, this line defines a method named load transactions within the Neo4j class. This method takes one parameter, the high amount threshold, which is expected to be a numerical value. The purpose of this method is to construct and execute a cipher query that retrieves transactions from the Neo4j database, which either is marked as fraudulent or have an amount greater than specified, the specified high amount threshold. Moving on to the line 41, this line begins a multi-line string, which is in this context used for our cipher query. The F syntax indicates that this is an F string, which means that the exception inside the curly braces within the string will be evaluated at runtime. This allows for inclusion of Python expressions within the string, which is in this case used to insert the value of the high amount threshold into the query. And in the line 42, this line is the beginning of our cipher query, and match is a cipher close that is used to search for pattern in the graph. Here it is searching for nodes in the graph that have the label transactions. These nodes are temporarily named T for using the reminder of the query. In the context of fraud detection system, each transaction node represents a single transaction record in the graph, and the line 43 is a continuous of our cipher query. And here this line uses a where clause, which is used to filter nodes that were found by the match clause. In this specific query, it filters the transactions node based on two conditions, t.fraud and the t.amount. The t.fraud equals sign true checks if the fraud property of the node is set to true, indicating a known fraudulent transaction, and the t.amount greater sign and between the curly brackets high amount threshold checks if the amount property of the node is greater than the value specified by the high amount threshold, which is passed as a parameter to the load transaction method or method. The or logical operator between the conditions mean that the nodes satisfying either of two conditions will be included in the result set. And the line 44 here, this is the third part of our cipher query, which specifies what information should be returned from the nodes that match the earlier parts of our query. The return clause is used to specify the data that should be returned from the query, and the t.id as an ID indicates that the ID property of the transaction node should be returned in the result set. It should be aliased as an ID, and t.fraud as frauds indicates that the fraud properties of the transaction node should be returned in the result set and should be aliased as fraud. The t.amount as amount indicates that the amount properties of the transaction node should be returned in the result set, and it should be aliased as the amount. Finally, we have the line 46, which after constructing the cipher query string, this line execute the cipher query method. This line calls the execute cipher query method of the Neo4j connector class with the query string as an argument. The execute cipher query method is responsible for executing this cipher query on the connected node for Neo4j database and returning the result. The result of the executed cipher query method, which is a list of recorded representation of the transaction retrieved from the Neo4j database, are then returned from the load transaction method to the caller. Moving on to our data processor class in the line 48. Here we are defining a new class called the data processor that with the purpose of handling the process of raw transaction data that has been retrieved from the Neo4j database. It organizes and formats this data into a structure that can be used to train a graph neural network. The data processor class is assigned to work with three types of transaction: the known fraudulent transaction, high amount transaction, and all other transactions. And in the line 49 we have the init method for the data processor class, and this init method takes three parameters: the fraud transactions, the high amount, and the records. The fraud transaction is a list of transactions that are known to be fraudulent. The high amount is a list of transactions that have a high amount of volume greater than a certain threshold, which in this case we set it to 1 million, and a list of all transactions record to be processed. In the line 50 self.fraud transactions, this line assigns the value of the fraud transaction parameter to the instance variable self.fraud transactions. In the data processor class, the fraud transaction parameter represents the transactions that are known to be fraudulent, as I told you before, and these transactions are stored as an instance variable so they can be used in another method within the class. And in the line 51 we are assigning the value of the high amount transaction parameter to the instance variable self.highAmount transactions. In the data processor class, the high amount transactions parameter it represents the transactions that have an amount greater than a certain threshold. These transactions are stored as an instance variable so they can be used in other methods within the class. And in the line 52, this line assigns the value of records parameter to the instance variable self.records. In the data processor class, the records parameter represents the entire set of transaction records that need to be processed. These records are stored in the instance variable so they can be used in other methods within the class. And in the line 54, this line defines a method named process data within the data processor class, and the purpose of this method is to process the raw transaction data and organize it into formats suitable for training our graph neural network. This includes creating node features, edge indices, and labels, as well as handling the class imbalance issues that we might have. And in the line 55, this line uses a list of comprehensions to extract the transaction IDs from the self.fraud transactions list, which is an instance variable containing the transactions that are known to be fraudulent. Each element in the self.fraud transaction is expected to be a tuple, where the first element is the transaction ID. The underscore is a conventional placeholder for a value that is being ignored. The resulting list, fraud transaction IDs, contains the IDs of all known fraudulent transactions. And in the line 56, the high amount transaction IDs, this line uses a list comprehension to extract the transaction IDs from the self.highAmount transactions list, which is an instance variable containing the transactions that have a high amount greater than certain threshold. Similar to line 55, each element in the self.highAmount transaction is expected to be a tuple again, where the first element is the transaction ID, and the resulting list, which is the high amount of transaction IDs, contains the IDs of all high amount transactions. And in line 57, we have the high amount of transaction IDs added to the fraud transaction IDs, and this line concatenates these lists. It then converts this list into a set to remove any duplicate transaction, since the transactions might both be fraudulent and high amount. Finally, converts the set back into a list, which is stored in the variable all transaction IDs. This list contains a unique ID of all transactions that are either known to be fraudulent or have a high amount. And in the line 58, this line uses a dictionary comprehension to create mapping from the transaction IDs to indices. The enumerate function is used to get both index and the transaction ID for each transaction in all transaction IDs. This mapping is stored in the dictionary transaction ID to index, where keys are transaction IDs and the values are the corresponding indices. This mapping will be used to efficiently look up the index of a transaction in the graph based on its ID. Moving on to line 59, fraud transaction indices. This line creates a list comprehension to convert the list of fraudulent transaction IDs into a list of corresponding indices in the graph. It does this by looking up each transaction ID in the transaction underscore ID underscore to underscore index dictionary. The resulting list fraud transaction indices contains the indices of all known fraudulent transactions in the graph. And in the line 60 here, similar to the line 59, this line uses a list comprehension to convert the list of high amount transaction IDs, which in this case is high underscore amount underscore transactions underscore IDs, into a list of corresponding indices in the graph. It looks up each transaction ID into transaction ID to index dictionary. The resulting list, which is the high amount transaction indices, contains the indices of all high amount transactions in the graph. And in the line 61, this line indicates the creation of the torch.tensor named edge index in the context of graph neural networks. The edge index tensor is used to define the connections or edges between the nodes in the graph. The tensor will have two rows. First row contains the indices of source nodes, and the second row contains the indices of the target nodes for each edge in the graph, where opening a bracket indicates that the list is being started, which will be passed to the torch.tensor constructor. And in the line 62, the line 62 is a continuation from the line 61, and the list of indices for fraudulent transaction is concatenated with the list of indices for high amount transactions. This concatenated list will become the first row of the edge index tensor, representing the source of nodes of edges in the graph. And in line 63, we are passing the torch.tensor constructor, and in this line we are creating a list of zeros with the same length as fraudulent transaction indices, and this part meant to represent the fraudulent transactions that are connected to a specific type of node, in this case the fraudulent label node. And after that, that says plus between the brackets 1 multiplied by len high amount transaction indices. This creates a list of ones with the same length as high amount transaction indices. This part means to represent the high amount of transactions that are connected to another specific type of node, the high amount label node. This entire list will become the second row of the edge indices tensor, representing the target node of the edges in the graph. And in line 64, this line completes the torch.tensor constructor call started in the line 61. The d type equals sign torch.long argument specifies that the element of the edge index tensor should be of the long int 64 data type. This is common for indices in PyTorch. After this line, the edge index tensor is fully constructed and contains the information about the connections between the nodes in the graph. And in the line 65, this line creates a torch.tensor named X, which serves as a node features matrix for the graph neural networks for each transaction in the self.records, and it kind of assumed to be a list of tuples. It extracts the amount field, the third element in each tuple in this case, and creates a new list with these amounts, where each amount itself inside a list to make it a 2D structure. This 2D list is then converted into a PyTorch tensor with the data type of float. And in the context of graph neural networks, X is a common name for node features matrix, and it is kind of a standard. And in the line 66, the num_nodes, here this line calculates the total number of nodes in the graph by taking the length of all transaction IDs list, which contains a unique ID for all transactions that are either known to be fraudulent or have a high amount. The resulting integer is stored in the variable num_nodes. And in the line 67, we create a PyTorch tensor named Y filled with zeros and of shape of num_nodes, where num_nodes is the total number of nodes in the graph as calculated in the line 66. The data type of the tensor is set to long. This tensor will be used to store labels for each node in the graph, where the label indicates whether a transaction is fraudulent or not. And in the line 68, we begin for a loop that iterates over each index in the fraud transaction indices list. The variable IDX represents the current index for known fraudulent transactions in the graph. The fraud transaction indicates a list that was created earlier and contains the indices for all known fraudulent transactions in the graph. And this loop is used to assign appropriate labels to these transactions in the Y tensor, indicating that they are fraudulent. And moving on to the line 69, inside the loop, this assigns the value 1 to the Y tensor at the position specified by the current index IDX. In the context of binary classification, a label of 1 typically represents the positive class, where it is used to indicate that the transaction is corresponding to this index as fraudulent. Thus, for each known fraudulent transaction, its corresponding position in the Y tensor is marked with 1. And in the line 70, fraud indices, here this line uses a list comprehension with the conditional statement to create a new list named fraud indices. It iterates over the Y tensor, which contains the labels for each node in the graph, and for each element it checks if the label is equal to 1, and if the transaction it is marked as fraudulent. So as I explained to you before, the enumerate function is used to get both index I and the label for each element in the Y tensor. If the condition label double equal sign 1 is true, the index I is indicated in the fraud indices list. This list will thus contain the indices of all transactions in the graph that are labeled as fraudulent. Moving on to the line 71, this line is addressing the class imbalance problem by oversampling the minority class, which in this case is the fraudulent transaction, the label 1, and the fraud indices list contains the indices of all fraudulent transactions. To create more copies of these fraudulent transactions, the fraud indices list is replicated a certain number of times, which is calculated by the expression. The expression is num_nodes /len up until the -1. Here this expression calculates how many times the fraud indices list needs to be replicated to approach a balance between two classes. The resulting oversample indices list contains the indices of fraudulent transaction separated multiple times. Moving on to the line 72, here we use the torch.cat function to concatenate original node feature matrix X with additional copies of the features of fraudulent transactions. The additional copies are selected from the original X tensor using the oversample_indices list created in the previous line. The dim equals sign 0 argument specifies that the concatenation should be done along with first dimension, which is rows, if you don't know, effectively adding more rows to the X tensor. This oversampling technique increases the number of fraudulent samples in the dataset, helping to migrate the class imbalance problem. And in the line 73 here, similar to line 72, actually pretty similar, this line oversamples the labels of fraudulent transaction to match the oversampling done on the feature matrix X. It concatenates the original label tensor Y with additional copies of labels of fraudulent transactions selected using the oversample indices list. The dim equals sign 1 0 argument specifies that the concatenation should be done to the first dimension, and if you forgot, the first dimension is rows. And in the line 74 num underscore nodes, after oversampling the number of nodes in the graph, has effectively increased. This line is supposed to update the num nodes variable to reflect new total number of nodes, both original and oversampled in the graph, by taking the length of the updated Y tensor. And in line 75 here we create an instance of the data class from the Torch geometric.data module and assigns it to the variable data. The data class is used to represent a graph in PyTorch geometrics, a library for deep learning on graph. In this line, the constructor of the data class is called with 3 arguments: the x equals sign x, the node feature matrix, which is the PyTorch tensor that contains the features for each node in the graph. So keep that in mind, x equals sign x. In it, each row corresponds to the features of a specific node, and edge underscore index equal edge index. Here we have the tensor defining the connection or edges between the nodes in the graph, and y equal y is the label tensor which contains the labels for each node in the graph, whether a transaction is fraudulent or not. And this data object now contains all necessary information about the graph, including the node features, edge connections, and node labels, and will be used as an input to the graph neural network. Moving on to the line 76, here we create a PyTorch tensor named train mask filled with zeros and the shape of num nodes, where num nodes is the total number of nodes in the graph as updated after oversampling. The data type of tensor is set to bool, which is the boolean, indicating that this tensor will be used as the binary mask. This train mask is intended to specify which nodes in the graph will be used for training the graph neural network. Moving on to the line 77, here we have again the train mask, and here we want to update the train mask tensor to specify which node will be used in the training set. It sets the first 80% of the elements in the train mask to 1 or true if you don't know, based on the calculation int 0.8 multiplied by num nodes. This means that the first 80% of nodes in the graph will be used for training, and as indicated by the true values in the train mask. Moving on to the line 78, here we want to assign the train mask tensor created and updated in the previous 2 lines to the train mask attribute of the data object. This attribute is part of the data class in PyTorch geometrics, and it is used to indicate which nodes in the graph should be included in the training set when training the graph neural network. Moving on to the line 79, here we want to create again a PyTorch tensor named test mask filled with zeros and the shape of num nodes with the data type of bool. This mask is indicated to specify which nodes in the graph will be used for testing the graph neural network. So again, in the line 80 we have the train mask again, but here we want something different. We want to update the train mask tensor to specify which node will be used in the test set. It sets the elements starting from the int 0 multiplied by nodes to the end of the tensor to 1, which is true and this means that the last 20% of nodes in the graph will be used for testing as indicated by the true values in the task mask. And in the line 81, here we want to assign the task mask tensor created and updated in the previous two lines to the task mask attribute of the data object. This attribute is part of the data class in PyTorch geometrics, and it is used to indicate which nodes in the graph should be included in the test set when evaluating the graph neural network. And finally, in the line 82, we have the return data, which marks the end of the process data method in the data processor class. It returns the data object, which is an instance of the data class from the torch geometric.data module. And this object contains all necessary information about graph, including the node features, edge connections, node labels, and the mask for training and testing set, which will be used as an input to train and evaluate the neural network. Moving on to our model builder class. Here in the line 84, we define our model builder class that encapsulates the neural network architecture and the process of initialization and the training the model. Moving on to the line 85, here we have the class net. This line defines a nested class named net within the model builder class. The net class inherits from the torch.nn.module, which is the base class for all neural network modules in the PyTorch, and the net class defines the architecture of the graph neural network that will be used for fraud detection. And in the line 86, here we want to initialize the method for the net class. The init method is a special method in Python that you have to know about before watching this video, because this video isn't for people that don't know programming. And the init constructor is called when an object is instantiated from the class. In this case, the constructor takes parameters in num node features, which is an integer representing the number of features for each node in the graph. This parameter is used to specify the input dimension of the neural network. Moving on to the line 87, the super method that we have. This line calls the constructor of the base class torch.nn.module using the super function. Again, super function is very well known in the Python programming community. This is a necessary step when you're subclassing a PyTorch module. It ensures that the net is properly registered as PyTorch module and that it can access all methods and properties of the torch.nn.module class. Moving on to the line 88, we have self.conv1. This line creates an instance of the GCN conv class from the torch geometric.nn module and assigns it to the instance variable self.conv1. GCN conv stands for Graph Convolutional Network Layer, and it is one of the most fundamental building blocks for graph neural networks in PyTorch geometrics. In this line, the GCN conv layer is initialized with two parameters, num features and the 32. Here, the num node features is the number of input features for each node in the graph, which is passed from the constructor. And the 32 is the number of output features or channels for this layer. This means that after this layer, each node in the graph will have 32 features. Moving on to the line 89 here, this line creates another instance of the GCN conv class and assigns it to the instance variable self.conv2. This is the second graph convolutional layer in the neural network. It initialized with two parameters, again the 32 and the number of output features, which is the 16, but the 32 is the number of input features for each node, which matches the number of output features from the self.conv1, and the 16, if I want to explain to you clearly, the number of output features or channels again, and for this layer, and after this layer each node in the graph will have 16 features. So pretty simple stuff. And moving on to the line 90, this line creates yet another instance of the GCN conv class and assigns it to the instance variable self.conv3. This is the third graph convolutional layer in the neural network. It is initialized with two parameters, 16 and 2. The 16 is the number of input features for each node. I think you kind of guessed it, which matches the number of output features from the self.conv2, and the 2 is the number of output features or channels for this layer. After this layer, each node in the graph will have two features corresponding to the two classes, the fraudulent or not, in the binary classification classification task, and it will continue with the explanation of the subsequent line in the binary classification task. Moving on to the line 92. Here, this line defines the forward method for net class. The forward method specifies how the input data flows through the layers of the neural network and what operations are performed on it. In PyTorch, the forward method is automatically called when you pass data through a model instance. The data parameter here is expected to be an instance of the data class from the torch geometric.data module, which contains all necessary information about the graph, including the node features, edge connections, and the node labels. Moving on to the line 93, and we have pretty similar lines, but they all perform different operations. The line 92, to be specific, extract two important components from the data object that was passed as a parameter to the forward method. The X is the node feature matrix, and X is a standard for using it as the node feature matrix. This is kind of a standard in programming community, and X is a PyTorch tensor containing the features for each node in the graph. Each row corresponds to the features of a specific node, and the edge index is the PyTorch tensor defining the connections, and the connections are edges between the nodes in the graph. And moving on to the line 94, here we have the node feature matrix X and the edge connections, edge index through the first graph convolutional layer. Self.conv1 of our neural network, the GCN conv layer, takes the node features and the graph structure defined by the edge index as an input, and it performs the graph convolutional operation and updates the node features. The updated node features are then assigned back to the variable X. And moving on to the line 95, here f.relu and X as an argument. Here this line applies the relu refactor linear unit activation function to the updated node features X after passing through the first graph convolutional layer. The relu activation function is defined as f with the argument of X equals sign max with the argument of 0 and X. This is a formula which means that it replaces all negative values in the X with zeros. The relu activation function is a common choice for introducing non-linearity into neural networks. f.relu is a function from the torch.nn.functional module, which is often imported as f. And if you can remember, in the line 96, here we have the X equals sign f.dropout. Here we want to apply the dropout to node features X. Dropout is a regularization technique used in neural networks to prevent overfitting during the training. Dropout randomly sets the fraction of the input unit to 0 at each update, which helps to prevent overfitting. The training equals sign self.training argument specifies whether the model is in the training mode, which in this case self.training is true, or evaluation mode, which is the self.training is false. In the evaluation mode, dropout is effectively turned off. So I think that was a clear explanation of this line because it's a bit tricky. And in the line 97 here, this line passes the node feature matrix X after the relu activation function and dropout, keep that in mind, and the edge connection, which is the edge index, through the second graph convolutional layer self.conv2 of the neural network. Similar to the first graph convolutional layer, this layer updates the node features based on a graph structure, and the current node features is the updated node features that are assigned back to the variable X. Here in the line 98, similar to the line 95, here this line applies the relu activation function to the updated node features X after they have passed through the second graph convolutional layer. This introduces a non-linearity to the activation of nodes in the graph. Moving on to the line 99, here we have the node feature matrix X after again the relu activation function applied and the second layer from the second layer, and the edge connections through the third and final graph convolutional layer self.conv3. And in our total neural network, as the previous layers, this layer updates the node features based on the graph structure and the current node features. The updated node features are then assigned back to the variable X, and in the line 100 the return f.long softmax, which gets the x and dim1. Here we want to apply the long softmax activation function to output the third graph convolutional layer. The updated node features of x is what we want. The softmax activation function converts the raw output scores, also known as logits, sometimes called, for each node into probabilities, and the long function is then applied to these probabilities. The dim1 argument specifies that the softmax should be computed along with dim1, which is across the features of each node. This is the final output of our neural network, and it represents the long probabilities of each node in the graph belonging to each of the two classes, fraudulent or not. The method then returns the tensor of the long probabilities as its output. And in the line 102, here this line we define an init method for model builder class. The init method is also known as constructor, as I told you, and the constructor takes one parameter here, the data, which is an instance of data class from the PyTorch geometric.data module, which contains all necessary information that we need about graph, including the node feature, edge connection, and node labels. This data object will be used as an input to the graph neural network. And in the line 103 self.data, we assign the data parameter passed to the init method to the instance variable self.data. This makes the data object accessible to other methods within the model builder class, allowing them to use graph data to build and train the neural network. Moving on to the line 105, here we define a method named buildModel for the model builder class. This method is responsible for building, initializing, and training the graph neural network model for fraud detection purposes that we want. It takes no parameter besides self, which is the reference to the instance of the model builder class that this method is being called on. In the line 106, this line, you are probably familiar with this line because it chooses the CUDA or CPU for processing, and it is the PyTorch device object, which represents the device on which PyTorch tensor will be allocated. The torch.CUDA is available function checks whether the GPU is available. If it's so, the device is set to CUDA, including that the component should be performed on the GPU. If no, the GPU is available in our device, the device is set to CPU, indicating that the computation should be performed on the CPU of our device. And moving on to the line 107, here the modelbuilder.net instantiate the net class defined earlier within the model builder class. It passes the number of node features in the graph data, the self.data.numNodes features, as an argument to the net class constructor. This creates a new instance of the graph convolutional layer model with the appropriate input dimension. .toDevice moves the model to the specified device, either GPU or CPU, as determined in the line 106. This ensures that all computation involving this model will be performed on the designated device that we want, and here the model gets the newly created device. Moving on to the line 108, this line moves the data object, which contains the graph data, to the specified device, again either GPU or CPU. Moving on to the line 109, here we initialize a variable named num classes and assigns it to the variable 2. This variable represents the number of output classes for binary classification problem that the graph neural network is trying to solve. In this context, the two classes represent whether the transaction is fraudulent or not by using 1 or 0. So keep again that in mind. If you forgot, they are evaluating everything based on 1 and 0, and we have a binary situation right here. In the line 110, here this line constructs a list named class count, which contains the count of instances for each class in the dataset. It does this through a list comprehension, which iterates over each class index I from 0 to num classes minus 1, in this case 0 and 1. So as I told you, for each class index I, it computes the sum of the instances where the label self.data.y, which is the label tensor from the graph data object, and here here is equal to I. As a result, the class count will be a list of two elements, the count of non-fraudulent transaction and the count of fraudulent transaction. So clearly you can understand these are not very sophisticated. And in the line 111, here this line constructs a list named class weight, which contains the inverse of the counts of instances for each class in the dataset with a small constant 1e minus 10. Here added minus 10 added for numerical stability that we want. The purpose of these classes and weights is to handle the class imbalance during the training of the model. By using these weights in the loss function, our model will give more importance to underrepresented classes. For example, if a fraudulent transaction are rare, their corresponding weight will be higher, making the model more sensitive to errors on those instances. And in the line 112, here we want to convert the class weights list created in the previous line to a PyTorch tensor with data type torch.float. It then moves this tensor to the specified device, either CPU or GPU, determined earlier. The resulting tensor assigned to the variable weights will be used in the loss function during the model training to handle class imbalance. Moving on to the line 113, here we want to initialize an Atom optimizer for the torch.optim module and assigns it to the variable optimizer. The Atom optimizer is a popular optimization algorithm and it is pretty useful in neural networks. The model.parameter method call return on iterator over the model parameters, the weights and biases, which the optimizer will update during the training, and the learning rate is set to 0.005 and the weight decay parameter is set to 5e-4, which is a form of L2 regularization that helps prevent overfitting. So if you don't know these things, just Google them and you learn them very quickly. So the line 140, the criterion, here we want to initialize a negative likelihood NNL loss function from the torch.nn module and assigns it to the variable criterion. The NLL loss is commonly used in classification problems along with softmax as a final layer of activation, which we use it right here. This is a right place to use it. The weight parameter is set to the weight tensor created earlier, which contains the class weights. This allows the loss function to give more importance to underrepresented classes, helping to migrate class imbalance during our training again. And in the line 115, here we want to set the model training mode. In training mode, certain layers of the model, likelihood dropout and batch normalization, behave differently than they do in the evaluation mode, calling the model.train to ensure that these layers are in the correct state during the training. And this is a standard practice in PyTorch when you are about to train your model. Moving on to the line 116, here this line marks the beginning for the loop that will iterate for a total number of 200 times. Each iteration of loop represents one epoch of training. During each epoch, the entire training dataset is passed through the neural network once, and the model parameters are updated based on the computed loss. The number 200 is a hyperparameter that specifies the number of training epochs. Moving on to the line 117, at the beginning of each epoch, this line represents all gradients of the model parameters to 0. In PyTorch, the gradients are accumulated across operations during the forward pass, so it's essential to zero them out at the start of each iteration to avoid accumulation gradients from previous iterations. This is a standard step in the training loop of the PyTorch model. In the line 118, here this line performs a forward pass of our graph data through the neural network model. It calls the forward method of the net class and net class with self.data as an argument. The self.data object contains the node features, edge connections, and labels for our graph, and the output will be assigned to the variable out. This is a tensor of long probabilities for each node in the graph. Moving on to the line 119, we have the loss equals sign criterion. This line computes the loss for the current batch of data using the negative likelihood loss function, also known as criterion, that was initialized earlier. the out expression selects the log probabilities that correspond to the nodes in the training set as specified by the training mask in the self.data object, and self.data.y selects the true labels for those nodes. The criterion function then computes the loss between these predicted log probabilities and true labels. This represents how well the model prediction matched the actual data and is the value that we aim to minimize during the training. And in the line 120, loss.backward, here the loss function with the respect to each parameter. Here this line computes the gradient of loss function with respect to each parameter in the model using the backpropagation algorithm. These gradients represent how much the loss would change if the parameters were adjusted. This is a critical step as these gradients are used by the optimizer to update the model parameters. And in the line 121, optimizer.step, after the gradients have been computed by the loss.backwards call, this line updates the model parameters, weights and biases using the optimizer step function. In this case, the optimizer is an instance of the Adam optimizer that was initialized earlier. The step function adjusts the model parameters in the direction that reduces the loss based on the previously computed gradients. This is the point which the model actually is learning from. And moving on to the line 122, here this line remarks the end of the build model method within the model builder class, and it returns us a model after completing the specified number of training epochs and updating the model parameters based on the training data. Moving on to the line 124, class model evaluator. This line defines a new class for us, model evaluator, and this class is responsible for evaluating the performance of the trained graph neural network model on a separate dataset that model has not seen during the training, typically called the test set. The purpose of this evaluation is to estimate how well a trained model is likely to perform on unseen data, which is pretty crucial for understanding the model ability to generalize new unseen examples. And in the line 125, we have the initializer here, which is a method in Python, and it will get called when you create a new instance class. Here it gets the model. This is a trained neural network model that we have right now. In this line, model will be used in the model evaluator class. The data is here in the line 124. We have the model evaluator class. This line defines a new class named model evaluator. This class is responsible for evaluating the performance of our model. Moving on to the line 125, we have the initializer. In this case, takes two parameters, the model and the data. This is the trained neural network. The model and the model evaluator class will be evaluating this model based on various factors, and the data is an instance of the data class from the Torch geometric.data module, which contains all necessary information that we need. For example, the node features, graph and edge connections, node features, graph information and edge connections, and the node labels. And in the line 126, this self.model assigns the model parameter passed to the init method to the instance variable self.model. This makes the trained neural network model accessible to other methods within the model evaluator class. And the line 127 assigns the data parameter passed to the self.data. Here is pretty similar to the line above it, and makes the data accessible to other methods within the model evaluator class. And in the line 129, the model evaluator, the def evaluate, which gets self. Here, this method is designed to evaluate the performance of the trained model on the test set. It does not take any parameters other than self, which is a reference to the instance of the model evaluator class that is being called on. Self.model.eval. This sets the model evaluation mode to an evaluation mode, creating layers of models like dropout, batch normalization, and here they behave differently than they do in the training mode. node. Calling self.model eval ensures that these layers are in the correct state during the evaluation process. This is a standard practice in PyTorch. Moving on to the line 131, the underscore and perd, the line that has the underscore in the beginning. And if you don't know what this underscore is, have to have a solid understanding of programming. This line performs the forward pass of the graph data through the neural network model for the purpose of making predictions. The self.model part calls the forward method of the net class with the self.data as an argument. The self.data object contains the node feature, edge connection, and the labels for the graph. The .max dim equal sign 1 operation is then used to find the class with the maximum log probabilities for each node. This results in two values. This function will return us two values, the actual maximum log probabilities and the indices of the maximum log probabilities, which are equivalent to the predicted class labels. Moving on to the line 132. Here in this line we want to assign the test mask attribute from the self.data object to the variable test mask. The test mask is a Boolean tensor that specifies which node in the graph are part of the test set. This mask is used to select only the test node when evaluating the model performance. Moving on to the line 134, we want to extract the true labels of the nodes in the test set and convert them to NumPy array. So self.data.y accesses the node labels from the self.data object. Test mask uses the Boolean test mask to select the labels from only the nodes that are part of the test. The .cpu moves the selected labels to the CPU, and .numpy converts the PyTorch tensor of true labels to a NumPy array. This is if you wondering why I did this, this is done to make it compatible with the scikit-learn matrix functions used later. The resulting NumPy array, which contains the true labels of the test nodes, is assigned to the variable true labels. So that was the reason why I did that, if you're wondering. And in line 135, this line extracts the predicted labels of the nodes in the test set and converts them into a NumPy array, similar to what was done for the true labels. The perd tensor contains the predicted class labels for all nodes, and the test mask is used to select the predictions for only the test node. The predictions are then moved to the CPU and then converted to a NumPy array, and the resulting array is assigned to the variable perd labels. Moving on to the line 137, which is pretty much the last important line of our code right here in the model evaluator class. Here we have an if statement, and it checks whether the sum of the perd label is equal to 0. In the context of binary classification problem that we have here, represents a positive, or if you're paying attention, a fraudulent transaction or fraudulent situation, and the 0 represents a negative, which is a non-fraudulent class. This condition checks that for us, which is pretty crucial. Here these lines from 137 up to line 147 are pretty important, because if the model predictions have no positive sample, certain matrices like the precision, recall, and an F1 score usually require no positive samples. Certain matrices like precision and recall would be undefined, as they require a true positive prediction. So in the line 138 we have a printf statement that, if no positive has been found, prints a message for us in the terminal. The line 139 we have the precision, recall, and F1 set to 0, and we have an else statement in the line 140 up to line 143. If we had a positive sample, the precision, recall, and F1 score will be printed to the terminal using the line 145 to line 147. So let's close it and move on to the anomaly finder. This is a pretty short and simple anomaly finder class. This usually in a real world scenario is pretty complex, contains multiple parts, and this should be a very sophisticated class. But here, because you are a beginner and you just want to understand how how such a system works. I made it very short and simple, so let me explain to you each and every single one of them. In the line 149, here we defined the Anomaly Finder class, which we want this class to identify anomalous transaction based on predictions made by the trained neural network model in the context of fraud detection that we have in this script. An anomaly refers to a transaction that is suspicious of being fraudulent based on a certain pattern or behavior, especially the client behavior right here is pretty important, and we need to design a very good pattern predictor class. And in the line 150 we have an init method that is constructor for getting called when you create a new instance of a class. In this case we have two parameters on it, the model and the data, which you know what both of them are. The data is the edge connection, node features, etc., and the model is our trained neural network. In the line 151 self.model, here again pretty similar to other lines that I explained to you, the self.model instance variable will now hold the trained model that will be used to find anomalies. And in the line 152, here we want to make data accessible to this class, and in the line 154 we define a find anomalies function, and this method is designed to apply the trained model to the graph data and identify the nodes which are the transactions that are predicted based on the anomalies, the potential frauds that we want to get at the end. It does not take any parameters other than self, which is a reference to the instance of the anomaly finder class that this method is called on. And in the line 155, here this line sets the evaluation mode. In the evaluation mode, certain layers of the model, as I explained to you, like dropout, batch normalization, behave differently than they do in the training mode. So let's move on to the line 156. Again, we have the same line in the model builder. I don't think it needs an explanation. If you didn't understand, go back the video and watch it. And in the line 157 we have the anomalies. Here this line identifies the indices of the nodes, the transactions again that we have in the test set that are predicted to be anomalies, and it gets the paired self.data.test mask, a non-zero, and a toList method. I will explain to you each of them in brief. The self.data.test mask is a Boolean tensor specifying which nodes in the graph are the part of test set. The non-zero finds the indices of the elements in the tensor that are non-zero, and the toList converts the resulting tensor indices to a Python list. The resulting set, which contains the indices of the nodes in the test set that are predicted to be fraudulent, is assigned to the variable anomalies. And the line 159 returns us the anomalies. This is not going to work and find any anomalies for us right now, and I told you it has a reason, because if I want to write down an anomaly finder, it's going to be very sophisticated and very time consuming, but it's not that difficult if you are around the team and you're doing your daily job and you know programming, of course. And here, after identifying if there was an anomaly or not, this class will be returned, and we are going to get our anomalies or we are not going to get any anomalies. And in this case, as I told you, we are not going to get any anomalies. And let's move on to the bubble graph that we have here. The bubble graph class is a class that we want to get after running the code, and you will see the bubble graph in a minute that will show us everything about our dataset in a visualization format. Here we created a class named bubble graph, and in the line 162 we have the initializer that gets the fraud transaction and high amount transactions. The fraud transaction is expected to be a list of transactions that are known to be fraudulent, where each transaction is represented as a tuple containing the transaction ID and the amount involved in the transaction. And the high amount transaction is expected to be a list of transactions that have a high amount of transaction that we think maybe they are fraudulent. Moving on to the line 163, self.fraud transactions. Here this line assigns the fraud transactions parameter passed to the init method to the instance variable self.fraud transactions. This makes the list of known fraudulent transactions accessible to other methods methods within the bubble graph class that we have. And in the line 164, we want to assign the high amount transaction parameter passed to the init method to the instance variable self.highAmount transactions, and to make it accessible to other methods within the bubble graph, similar to the last line. Moving on to the line 166, we define a method named createGraph for the bubble graph class. This method is designed to create and display a bubble graph visualization based on known fraudulent transaction, high amount transactions, and the anomalies predicted by the model. Moving on to the line 167, we want to use a list comprehension to extract transaction IDs from the self.fraud transaction list and assigns them to the variable fraud transaction underscore x. Each element of the self.fraud transaction is expected to be a tuple containing a list of transaction IDs and an amount, and the underscore in the list comprehension is a conventional placeholder for a value that is being ignored, in this case the transaction amount. And in the line 168, fraud underscore transaction underscore y, here we use a list comprehension to extract transaction amount from the self.fraud transaction list and assigns them to the variable fraud transactions y. Each element of the self.fraud transaction is expected to be a tuple containing transaction ID and an amount. The underscore in the list comprehension is a conventional placeholder for a value that is being ignored, in this case the transaction ID. And moving on to the line 169, here these two lines are pretty similar, the 69 and 70. Here each element of the self.highAmount transaction is a tuple containing the transaction ID and amount. And moving on to the line 170, the self.highAmount transaction list is being assigned to the high amount transaction y. And I wrote down these couple of lines for you if you want to make the bubble size the size of transaction, but I did it and it wasn't a good visualization report, so I disabled them. But if you want a bubble based on the transaction amount, you have to use these lines. And the line 172, the fig variable that we have here, we want to create an empty figure object using the figure class from the plotly.graph objects module that we imported in the, I think, line 6. And this figure object is plotly used to create and manage different types of plots and visualization. In this context, fig will be used to assemble the bubble graph visualization of the transactions. In the line 174, we want to add a new scatter plot trace to the fig object, which will be used to visualize the known fraudulent transaction in the bubble graph. The go.scatter class is used to create a scatter plot in the plotly. The argument passed to the go.scatter specifies the properties of the scatter plot, such as the x and y coordination of the points or bubbles in their color and their name. In the scatter plot, the x equal fraud transactions specifies the x coordination of the bubbles, which are set to the transaction IDs of the known fraudulent transaction. Y per similar specifies the size of the bubble, which are set to the amount of known fraudulent transactions. Mode equal markers indicates that the plot should show markers or bubbles at the specified x and y coordinations, and marker dict color red sets the color of the bubble to red, making the known fraudulent transaction clearly visible on the final visualization. The named proven fraud, it's pretty obvious. And moving on to the line 182, we want to add another scatter plot to trace the figure object, which will be used to visualize the transaction that are suspected to be fraudulent due to the high amount in the bubble graph, similar to the previous scatter used for the known fraudulent transaction. This is now for the transaction with the high amount. The arguments passed to the go.scatter specifies the properties of this scatter plot. So pretty similar. Also the line 197 up to line 202. These are pretty similar lines. There's not really a big difference between them, so I'm sure you will understand. And let's go through the main. And before we move on to the main function, if you're wondering, the fig show, this line calls the show method on the fig object, which will display an assembled bubble graph visualization in the output. So this one was again pretty obvious. Here in the line 207 we have a main function. This line defines a main function for us. The main function is a conventional name for the function that serves as an entry point to an script, so we have it right here. The line 208 creates a new instance of the Neo4j class for us, which is responsible for establishing the connection. And you probably remember the Neo4j URI, the user, the password that we wrote in the first part of the video right here. And the line 209 calls the connect method on the Neo4j connector object. The connect method is defined in the Neo4j connector class, attempting to establish a connection with Neo4j database using the credentials provided in the first part of the script. But keep in mind that those credentials should be in the separate file. And in the line 211 we have an if statement that checks whether the driver attribute of the Neo4j connector object is none. If it's none, this means that the connection to the Neo4j dataset is failed. And in the line 212 we use the logging module to log an error message that indicates a failure to connect to the Neo4j database. This line will be executed if the connection to the Neo4j database was not successful, as determined by the connection in the line 211. The line 213, this line immediately exits the main function if the connection to the Neo4j database was not successful. And in the line 215, this line calls the load transaction method on the Neo4j connector object with a high amount threshold parameter. And the records is a list of dictionaries where each dictionary represents a transaction record fetched from the Neo4j database. Each record contains the transaction ID, the fraud flag, and the transaction amount. In the line 216 we have the fraud transactions variable. Here we are using a list comprehension filter to filter and transform the list records. The list transform the record list, creating a new list named fraud transactions. Here in the line 217 again we are using list comprehension to filter and transform the records list, creating a new list called high amount transactions. In the line 219, this line calls the close method of Neo4j connector object. The close method is responsible for closing the connection. And in the line 221, here we check if whether both fraud transaction lists and the high amount transaction lists are empty. If both lists are empty, this means that the query to Neo4j database did not return any transaction that either was known to be fraudulent or have a high amount. And here in the line 22, the logging.info no anomalies found in the dataset will be printed. And the log here, this line uses a logging module to log an informational message that indicates that no anomalies, either known fraudulent or high amount transaction, were found in a dataset from fetching data from Neo4j database. This line will only be executed if both fraud transaction lists and the high amount transactions are empty, as determined by the condition in the line 221. Moving on to the return statement. This is pretty obvious, and the line 223 needs no explanation. Moving on to the line 225, here the data processor. This line creates a new instance of the data processor class, which is responsible for processing and preparing the transaction data for input into the machine learning model that we have. The parameters passed to the data processor constructor are fraud transaction, high amount, and record. And the line line 226, here this line calls the process data method on the data processor object. Then the process data method is designed to transform the raw transaction data into a format that can be used by the PyTorch geometric deep learning model. The data is an instance of the data class that we have, and in the line 228, the model builder. This line creates a new instance of the model builder class, which is responsible for building, training the graph neural network model for fraud detection, and it has that is data, which is an instance of the data class from PyTorch geometrics. Moving on to the line 229, here the build model method is responsible for defining the structure of the graph neural network, initializing it with the appropriate parameters, moving to a proper CPU or GPU. And in the line 231, here this line creates a new instance of the model evaluator class, which is responsible for evaluating the performance of the graph neural network model on a separate dataset. The model evaluator object will be used to calculate various performance matrices for the trained model, such as precision, recall, and a fun score. Moving on to the line 232, the model evaluator.evaluate method. This calls the evaluate method on the model evaluator object. The evaluate method is designed to put the trained model into evaluation mode. For example, if you don't understand, this ensures that dropout layers are not active during the inference. And moving on to the anomaly finder in the line 234, here we create a new instance of the anomaly finder class, which is responsible for using the trained model to identify anomalies, potentially fraudulent in this case, from the transaction in the test set of the transaction data that are potentially fraudulent. And it has two parameters, the model and the data. The model is our trained graph neural network, and the data is the processed graph data object. The anomaly finder object will be used to apply the trained model to the test set of the transaction in order to identify those that are most likely to be fraudulent based on their features and relationships in the graph. And in the line 235, we call the find anomalies method on the anomaly finder object to identify the transaction for which the model predicts on the high likelihood of fraud, the anomaly. Moving on to the line 237, the bubble graph. Here we create a new instance of the bubble graph class, which is responsible for visualizing transaction in a bubble format. And here we are passing things that we want to visualize, the fraud transactions, a high amount transaction into this method, and when a main function gets executed, this will run. And in the line 238, here we prepare the data necessary for the bubble graph, which indicates the x and y coordinates for non-fraudulent transactions, high amount transaction, and the predicted anomalies. So we have here create graph, which gets the anomalies as an argument. Pretty simple stuff. And the last two lines, the 240 and 241, here these two lines are a standard convention in Python, and here we want to check if the script is being run directly or not. And in the line 241, finally we are executing the main function and running the whole code all together. So let's run the code and see what we are going to get. After executing the code, here's the results that we are getting. As you can see, we have our red dots here. The red dots are proven frauds that we have, and the blue dots are the potential fraud that we might want to take a look at, and the black dot is a predicted anomaly that we predicted using the graph anomaly detection technique. Here we are getting a 0. This is normal, and in conclusion, if we want to take a look at the entire code, the provided Python script here outlines the comprehensive framework for building a basic fraud detection system using graph anomaly detection technique. This script is structured structured to be a clear and module code with different classes and function, each of them responsible for a specific task. And we first had our Neo4j connector, after that the data processor, the model builder, the model evaluator, and the anomaly finder, and the bubble graph, and finally the main function. Here each of them are responsible for different tasks, and by learning these techniques you can easily design fraud detection system for your project. I hope this video was informative to you and you learned something from it. If you have any question, put it down in the comments below. Thanks for watching, and I will see you in the next video.